Questo è solo per Zoom, non si sente meglio in stanza.
Okay. Grazie.
Okay, good morning everyone. I hope you had a nice weekend. So it's my pleasure to introduce to Andrea Triossi. He will be teaching FPGA programming with the VHDL for the full week. Yeah.
They're already on Git, I think.
Because I'm checking the timetable and I don't see the link.
Okay, I will let them know. Okay.
Okay, thank you, Felice. Do you hear me if I speak like that? Okay. So I introduce myself first of all. So I'm a professor at the University of Padua. I'm a physicist by degree, but then I took a PhD in computer science, and I worked mainly as a digital electronic engineer for some institute across Europe. And okay, I did a fellow also at CERN, and my interests are basically on the reconfigurable computing, so FPGA mainly. So I would like to understand from you instead what are your backgrounds, so just to understand better how to tailor the course. So are you all physicists? No, many engineer? No. So how many physicists first? Raise your hand. Okay. Engineer? Okay. Computer scientist? So the other, declare yourself, please. So who are you? No? Okay. Anyway, it's half and half with a bit of computer scientists. Okay. So usually engineers have more background on digital electronics than physicists. Physicists, they didn't do flip-flop. Like, okay, probably everybody knows Boolean port, the Boolean algebra, but maybe flip-flop and memory element, there are some missing parts. So if you will tell me if I have to cover more in deep that part that is for sure needed for this course. And so the course is basically an overview, an introduction of the FPGA programming. So I will also only give a basic notion of FPGA programming. I will start with today with a quick intro to the FPGA, so what they are used for, and how to program it, so the design flow of a firmware of an FPGA, because when we talk about FPGA, we don't talk about software and either hardware. It's a reconfigurable hardware, so it's called the firmware, what we install in the FPGA. So then we will see also the basic element inside the FPGA, not all of them. So also during the course, we will learn how to use some of them, the most useful one, but there are many other parties in the FPGA that can be configured and used in the design. So for programming the FPGA, we will see a programming language called VHDL. So we will not see the syntax or all the boring part of the programming code. We will only see example of code, so you could extract yourself the useful information from the code that I will provide you. And then we will also do some tutorials. So I will show you how to program the FPGA with my laptop, and then some exercise on your laptop. So when you will gain independence, you will start to program yourself the FPGA. So I expect that nobody has worked with FPGA till now. So, okay. At the end of the course, we will also try to do some, depends on how far we will go, but we can try to do also some full project, so real project, like a time to digital converter implemented in FPGA. That is an example of the use of the FPGA in front-end FPGA, so for front-end electronic. So another project that we can see is a protocol implemented in FPGA, simple protocol like UART. So we will see in detail this, and the goal is to implement this protocol yourself in the FPGA. So let's start to what are the FPGA. So let's start from the name, field programmable gate array. So the first part, field programmable, means that you can program the FPGA yourself. You don't need to ask to the manufacturer to program the device. So it can be reprogrammed as many times as you want, more or less. So that depends also on the family of the devices. There are mainly two families of FPGA. So there are the one based on static RAM cell that are, for example, the one from AMD and the one from Intel. So that are the two major brands of the FPGA. So they share mostly 80% of the market. Then there are also other devices like the one provided by Microchip, 10% of the market, that are flash-based. So it's another technology. What is the main difference is that so in the number of programming times, so the RAM based are you can program as many times as you want. The flash based has a small limitation on it, so we can program it thousands of times, not really as many times as we want. So then the other part of the name is gate array. Gate array means that it's really a matrix, physically a matrix of logic port gates. But this is, okay, it was the origin of the name. Nowadays, there are many other components inside the FPGA, not only logic gate. So we will see them. So let's start to what maybe you are more familiar, so a CPU. So what's the difference if I want to compare a CPU with an FPGA? So for sure, if I need, my application need low latency, I would prefer an FPGA rather than a CPU. So low latency and also determinism. So this determinism, maybe you can acquire it also on a CPU with a real-time OS or bare metal programming of a CPU. But the latency, it's not the same. There are order of magnitude of difference because even if in the CPU you probably use a faster clock for running the CPU, you needed to execute instructions, and the instructions are executed serially. And for each instruction, you need multiple clock cycles. So this takes long time to execute your program. In an FPGA, instead, you design the hardware in a completely parallel way. So this is the other point, the high degree of parallelism. So you design the hardware that you need for executing the algorithm that you want. So this can be optimized for parallelism. So and the latency. So the latency is the time that your device takes to process the data. So the time from the input data to enter and the output data to go out, it's much lower in the FPGA. Then also another good part of the FPGA is the connectivity, so the I/O of the FPGA. A CPU usually needs peripherals for connecting to the I/O. The FPGA has I/O block embedded in the device. So what are the drawbacks instead of using an FPGA? So unfortunately, programming an FPGA, it's much more time consuming. I would not say it's more difficult. It's more time consuming than a CPU. So software, it's easier than programming a firmware. Okay, so this we will see clearly. So another device that you could compare an FPGA is an ASIC. ASIC is it's an application-specific integrated circuit. So also this kind of device, it's an hardware meant for executing your program. But what is the main difference is that it's not reprogrammable, so it's not reconfigurable. It's a static hardware, so you need to send to the foundry your design, and then they will produce the chip and you can start to use it. So of course, this kind of device, it's much more performant with respect to an FPGA in the sense that you can achieve a much higher clock frequency. So the operation that you can do are much more. But the programming time, let's say, so the time that you need, that you spend from the design to the use of this device, it's much larger. So usually for programming an FPGA, a small design take a few minutes. Large design can be hours. For an ASIC, of course, you need much more time because you need the involvement of the producer of the chip. So this takes months usually. What is also another benefit using FPGA, it's the low entry barrier. What does it mean? That if you want to produce only few chip, this costs much less. So these are basically the idea is that if you want to use FPGA and you need only few units in your design, few sample of them, you start basically from zero, from the origin of the axis, and instead for the ASIC, you need to produce the mask that has to be printed on the silicon, and this has an initial cost. So then, of course, if the number of chip that you need it's larger, it's more convenient to produce an ASIC because the cost increase less than for FPGA. So what is the crossing point? So this depends on the kind of FPGA. So it depends on your design, if it is a big or small design. But usually it's in the order of thousands. So if you need more than thousands of units in your system, then it's worth to build an ASIC from the cost point of view. From the reprogrammability, for sure, still not. It's not convenient. Another point is that when you, so why I'm insisting with ASIC? Because also ASIC can be programmed with VHDL or Verilog, any other HDL language. If your design is purely digital, then you can use the same languages. Okay, so this is why it's important to compare them. But so you program it, but you program it only one time. So then the other benefit of the FPGA is that in the FPGA, the producer of the hardware made for you several parts of the circuit, of the hardware circuit. So for example, the reset distribution across the chip or the clock distribution across the chip is already designed and optimized for the design. While in an ASIC, you need to do it yourself. You need to have this infrastructure and produce it yourself. So, drawback of FPGA comparing to ASIC, the power. The FPGA is power hungry, so the reprogrammability has a cost in power. Not recommended for high volume, we already talked about it. Limited of operating frequency, so FPGA usually are programmed at, can run at the clock frequency of 100 of megahertz, few hundred of megahertz. The modern, the last generation, I think it's 500 megahertz, roughly the maximum frequency. While an ASIC can go up to gigahertz, few gigahertz. And of course, in ASIC, you can integrate digital and analog design, so your circuit can combine analog and digital part. In the FPGA, there are only digital blocks. There are exceptions. There are a few analog blocks, but we will see it's mainly for the generation of the clock, and there are no other analog components. So one important thing to understand, and that is basically the key message in programming FPGA. So that is basically the difference between programming a CPU, so software programming, and hardware programming like FPGA. Is that the program that we will write in VHDL is not executed by the device. Okay, the program is used for building a circuit that will execute later your program. So it will run the program, your circuit that you have programmed with VHDL. So it's basically a descriptional language. You use a language for describing a circuit, an hardware circuit. But you have to remember that every time that you write VHDL, you have to remember what are the hardware structure that will be inferred by the compiler by your code, okay, from your code. And then the circuit will process the data, the circuit that you will have built. So what we will see in this course, it's what we have said before. So FPGA programming flow, FPGA architecture today. And then we will start to use your laptop, the Vivado installation that you have in the laptop. So Vivado is the framework for programming AMD FPGA, that are the one that we will use in the course. We will see an example of hardware description language. We will see how to simulate your design. So simulate there are several steps we will see in a while of simulation. Then there are the two phases for generating a configuration of the FPGA, that are the synthesis first and then the implementation. We will see in deep also this in a while. And finally, maybe not today, but during the course, we will see also how to debug. So the debug is quite important, like for CPUs. But while in a CPU, the compiling time is so short that many times you compile and try and see if it works. With FPGA, it takes minutes, hours of compile time. You don't want to spend so much time in just an attempt. So simulation can help you in this, of course. But also a good debugging tool. It's important. Okay, let's go to the, please. Yes, so it's basically this part that takes a long time. So we will see in a while what consists this part. But behind this, there is basically a sort of Monte Carlo that has to be run for optimizing the circuit. So there are many resources inside the chip that can be used. And so there is the phase that is called mapping, so choose which resources you need, and the phase that is called routing, so connect the resources. There are many combinations, and this has to, it's finding a minimum, let's say, so it's an iterative process that the compiler has to do. So we will see better the next set of slides, what are the phases in the compilation. The program that the design that we will use in this course are small designs, so will not take more than a couple of minutes, the programming, the compilation time. So for the application, there are a lot. So FPGA, it's used in many fields, from medical to scientific instrument, military, a lot, unfortunately, automotive, audio application. So basically, wherever you need the low latency. So this is basically, I think, the key factor for driving the choice of an FPGA. It's the low latency. So you want, so let's try to quantify what does it mean low latency for us. Means tens of nanoseconds, something like this. So the clock cycle, it's roughly few nanoseconds. So let's assume that you need some clock cycle, not more than, I mean, some unit or tens of clock cycles. So we end up to have a latency of tens, hundreds of nanoseconds. This is something that it's not possible to achieve with the CPU, that we are in the ballpark of the microsecond latency. So this is mainly, so I can tell you, for example, an application that requires low latency, it's finance. So this is used in for buying, I mean, to spy from the network. The FPGA is used for spying for the network, the quotation of the market, and taking a decision buy, sell quickly before other can do it with the CPU. So this is required, for example, to decode the network stack, so UDP, EP, TCP, whatever is used, very, very quickly in short. So UDP can be decoded in one clock cycle in an FPGA. So 3 nanoseconds, 4 nanoseconds, you decode the UDP stack and the UDP EP, and you can run your algorithm for taking the decision. So this is just a funny example where you don't expect to find FPGA, but there are companies that does only this, basically. So what is interesting for us, it's physics, of course. So physicists use a lot FPGA. First of all, because it's reprogrammable, and physicists never have a clear idea what they want to do from the beginning. So it's an important feature, reprogrammability. But of course, because the latency, it's also important for the trigger. So trigger, it's I think that you are familiar with the concept of trigger. So it's a system that requires to take a decision quickly, because the readout in parallel has to buffers the data, and you need to take the decision if keeping or rejecting this data. So also DAX system actually not only trigger, let's say also the readout part of the system use the FPGA. This is mainly because of the high throughput that this device can have. So in the trigger system are used for the low latency, as we said. They are used as a collector in the trigger chain. So you have your detector that has many channels that has to be quickly analyzed by the trigger. So the FPGA are used first for forming the trigger primitive, for building the trigger primitive, so analyze this raw data, and then to combine all this channel and to run this trigger algorithm. Usually we the pipelined logic for having a short latency, and we needed to do it in parallel, in a very parallelized way with high degree of parallelization for achieving the latency. So just to give you an example, this is a card that is used in the trigger of CMS. It's a card based on a big FPGA that you see under the heat exchanger. So usually when you look at a card and you see a very big heat exchanger, it's where the FPGA sits because it's hungry, power hungry. So this is a card used for track finding, track fitting, basically, of in the muon chamber, in the barrel. But there are many algorithms that are usually implemented in the trigger algorithm that are usually implemented in the level 1 trigger, so the first trigger that run on hardware. On the other side, we have also FPGA used for data acquisition. So this is an example. I think this is in LHCb, PCI Express 40. So it's the current way of reading out of LHCb. So this it's an FPGA, also here a big heat exchanger, that is plugged in the PCI Express bus of a server. So, and then in the front panel, it has a lot of optical link to receive the data directly from the detector in case of LHCb, because they moved in a triggerless acquisition. So all the data are sent by optical link, received by FPGA, pre-processed. So usually at this level, you don't do a lot of pre-processing, but for example, compression or some other stuff can be done here. Usually you do it before sending the data, zero suppression, pedestal subtraction, for example, at the front-end level. So as we say, also at the front-end level could be an FPGA, please.
Sorry, these systems, do they use like also, do they have ADCs to evaluate the energy of the like the input charge, or they use like time over fresh algorithm, so they only care about the
So in this case, in the specific case, I think that here they do only collection. They don't apply algorithm here, because the task, let's say, it's to create a funnel of many links to one single server. And also just the decoding of these links, it's, I mean, need resources in the FPGA, because in the link they use also error correction mechanism, so the protocol is redundant. They use, in this case, they use the LPGBT link protocol. But there are other examples where here you do some pre-processing, like what you said, to unburden the CPU, basically. So to advance some task that, I mean, it has to be, let's say, simple task that doesn't require a lot of precision, for example, because we will see using FPGA in floating point is almost impossible, or let's say, no, it's not impossible. It requires a lot of resources that there aren't in the FPGA. So if there are simple tasks that can be done in fixed point, it's worth to advance the OS operation.
So in your opinion, it's like better not to do calibration FPGA?
Yes, probably fine calibration, it's not worth to do it. Yes, yes, definitely. So what we do now, it's a lot of machine learning algorithm. That's yes, because they usually not require the good precision. So 8-bit fixed point are enough for majority of classification tasks. But as I said, since floating point is not convenient to implement in FPGA, and also algorithm like I mean, make a derivative is not easy. Division, it's not easy to do it in FPGA. You use FPGA only for inference of machine learning, not for training. So there are few limitations in the use of FPGA. Okay, so this is was just to give an example of application of FPGA. I didn't say here another application that is to use the FPGA as an accelerator of a server. So use it as a coprocessor. So the CPU can decide to execute some operation in the FPGA and get it back, send the data on memory that can be in the hardware close to the FPGA. FPGA process the data, send it back. So this is what you do usually with the GPU, for example. There are also many applications of FPGA in this regards. Here I only present the FPGA instead in the, let's call it, streaming way of analyzing, elaborating the data. So in a chain of data flow, you put an FPGA for receiving input and sending out output. If you use it as an accelerator, usually what you do is you use only the PCI Express port for sending the data, writing on the memory present on the card. The FPGA read a batch of data from the memory, analyze it, and write the corresponding batch of data in output to the memory of the CPU. So why I'm not talking about this, not because this is not done, it's for sure done. It's just another way of using an FPGA. Let's say that for accelerator, the FPGA has many competitors because GPU, MPU, so there are now a lot of dedicated coprocessor. Instead, in a stream of data fashion where the FPGA is used for input and output in a chain, like in a trigger, there are no competitors at the moment for an FPGA. So it's let's say that the new competitor are all FPGA-based kind of device. You will see, for example, in this course, I think at the end of these 10 weeks, the AI engine that are dedicated sort of RISC processor dedicated for machine learning that are embedded in FPGA, because in any case, the FPGA part is used for interfacing the I/O. Okay, so this is it's an important part. The reprogrammability also of the I/O. Okay. Okay, so we can move to the other slide. And let's start with the design flow. So this is the main schema of the design flow of the FPGA. So we start from source file. So these are called RTL file. So register transfer level. So this is an historical, probably comes, from the beginning of the FPGA programming. Nowadays, it's hard to find code that really describe the register transfer level. So we will see actually a few of code, but usually the code, it's more behavioral. So it's more a code that describe what the hardware does rather than really describe how the hardware is implemented. But in many cases, still we use the RTL for doing some part of the circuit that are not easy to describe differently. So just to give you a rough idea, we will see later, but if you want to describe arithmetic operation, you usually don't start from the circuit of another, you just use the operator of addition. So this is basically the difference. But there are many tasks where you need to really design the circuit, and we will see also this the case of application of this. So RTL for us, it's VHDL basically. Can be VHDL, Verilog, these are the two languages most used. We will use VHDL. There are no many differences between the two. If you know VHDL, you are able to read Verilog and vice versa. There are both things are quite equivalent as languages. Other source files are IP, intellectual property. So what are these parts? So these are source files that usually can be encrypted or not. Usually are encrypted because are part of the code that can be given to you by the hardware manufacturer, for example. So AMD provide you a lot of IP. It's a code, a part of the code that usually it's customizable. So there is let's say a wizard that help you to customize this part, but you cannot see the VHDL behind this. So it's let's say a pre-digested part of the code, so that you can integrate in your circuit. So it's a sub-circuit for you that is provided you by third parties. And then we have the constraint. So the constraint file, it's something that you have to provide and depends mainly on the environment of the FPGA. So you have physical constraint for the FPGA, so the pin location, for example. But you have also other kind of constraint like timing constraint. So what is the time that the clock frequency that you want to run? So we will see in details also this kind of constraint, but it's basically another source file that has to be given to the other two steps that are synthesis and implementation. Okay. So synthesis, it's that we have to transform basically our source file, our VHDL, in what is called a netlist. So a netlist, it's actually our circuit described in terms of logic port and memory element, flip-flop mainly. Okay, so this is the output of the synthesis, the hardware circuit divided in logic and sequential operation, the flip-flop, and then we have the implementation that is actually choosing the resources that are needed in the FPGA for implementing the circuit. And finally, here at the end, we have our result of the compilation that is called bit stream. It's really a series of bits that are the configuration bit, actually. So that these bits are used for configuring the configuration memory, for programming the configuration memory of the FPGA. We have the possibility, as we said, of simulating our design, and we can do it in 3 different places, at 3 different levels. So we can simulate directly our VHDL. So let's see behaviorally what our VHDL does. We can do the simulation after the synthesis. So we can simulate the netlist, we can simulate the circuit produced by our synthesis. And we can simulate also the circuit after the implementation in our chosen FPGA, in our target FPGA. So what is the difference from here to here? That here we can simulate also the delay between the components, because now we know completely the routing between the element, and we know how much time is needed for passing the data from one component to the following one. So it's much more accurate. Of course, the simulation time increase in this case. So the simulation of the RTL is almost immediate, and this starts to take more time and can be minutes for the post-implementation simulation. Okay, so please, sure.
About the simulating part. So if you build a constraint file with like tiny constraints and you want to do a simulation, and in principle, with the tiny constraints, you are supposed to, even after the synthesis, if you do like that. Sorry,
please.
So I want to do a simulation.
Yes.
After a synthesis or after implementation. So after implementation, it takes longer. However, in theory, if you put the right time constraints, you are supposed to have a good circuit design also with ITL ports and everything. So is it better to do it after the synthesis or after the implementation? Because as I understand, it's safer to do after the implementation, but it takes longer.
Depends on the problem that you want to simulate, basically. So it's worth to start the behavioral, to check that your code behaves as you wish, basically. This is the first step to do. And could be that is the only one that you need. I mean, in the sense that if you check that the firmware behaves and does what you expect, you can stop the simulation at that level. Then you go through the synthesis, the implementation, you deploy in the FPGA, and you see that actually doesn't do what you wanted. So now, yes, it's time to simulate after synthesis or after implementation. So I would say that this is, I would go to the after implementation if you find the problem that is in hardware, in the sense that it's important to take into account the timing constraint. So it's important to know exactly why it is failing. We have to say that after the implementation phase, the compiler check that the constraints are met. So that the time that you declare that you want to achieve in the constraint file is actually met by the design. So if we trust the compiler, in principle, the implementation should close the timing. But the simulation is also done for checking this, actually, because this is not always the true. What is not always true? Why? Not because the compiler is not doing what it's expected to do, but it's because our constraint file, maybe it's not done perfectly. So sometimes in the constraint file, you can use this, and you must use this constraint that is called a false path. So false path means don't calculate the timing on this path. So it's a path that for me it's not important to close the timing. Can be a reset, for example, and asynchronous reset can be a false path usually, because you press a button and you don't want to be synchronized to your clock. It's asynchronous by definition. It could be that you have abused this false path and you have, by mistake, declared as false path many other paths that are actually should be synchronous. And this is the reason why the implementation closed the timing, but your design doesn't work. So coming to a simulation at this level will reveal this problem. Actually, there are no many problems that, let's say, that you spot in after synthesis. Not many problems. Well, the problem that you can spot in after synthesis is when you have. So your design behaviorally at RTL behaves correctly, but the synthesizer didn't understood it. So it understood wrong. I mean, you will see that in VHDL you have to use a predefined structure because the synthesizer has to map your code to an hardware primitive. If you use a code that is very fancy with different, I mean, it's not like the example design, let's say, the compiler can not interpret it correctly and generate a different circuit. So this is a case of error that you spot at this level.
So would you say if you have perfect timing constraints in general and your simulation fails at the implementation, and your
design,
your design fails, but the simulation was correct, so your constraints were wrong.
Yeah, usually yes.
Okay.
Usually yes, yes. Please.
I don't understand. For example, there's the RTL, IP, and constraints are these like the three inputs you need.
Yes. Well, not always all the three. So IP, it could be that there aren't in your design because it's a part of the circuit that is given you by a colleague, for example, that wants to pack all the source file in a single file, let's say.
So for example, the RTL will be the part you write.
Yes.
The IP is the third party.
Exactly.
The constraint
You're right.
You write when you get.
Also, this depends because if you buy an FPGA that is already mounted in a board, usually they provide you the constraint file, the manufacturer or the board, because either they give you the constraint file, either they have to give you the schematic because of the board, because you have to know each pin to what is connected. Because in the constraint file, you have the pin location. Basically, it's a constraint because every, let's say, every input of the FPGA can be mapped to a different pin. So you have the freedom of choosing it. So if I want to use this particular I/O connector, I have to know where it goes in the FPGA. So, and I have to declare in the constraint file the pin location.
For example, you have an RTL file that works for one FPGA and now you want to show them different FPGA.
Yes, I needed to change the constraint file. I can keep I can keep the RTL. Yes, I can keep the RTL. I can change only the constraint file. This is not true for the IP. So the IP usually are bounded to a specific FPGA. So if you change target FPGA, you need to change IP. Then also there is a caveat on the RTL in the sense that So there are two ways of describing the circuit. There is one that is more behavioral. That means I leave the compiler the freedom of inferring the hardware that I want to use. And this is portable. Let's say you change FPGA. If you have described it in this way, the compiler will infer another hardware that is given by the other FPGA, but it will infer it. It's more risky because we don't know if the hardware is available in the other FPGA or not. The other way is with instantiation. So you manually instantiate in your code the primitive that you want to use. In this way, you bound yourself to the use of a single FPGA, basically, because this primitive, if you move even if another AMD FPGA, but another family, the primitive change. So this gives you less freedom, let's say, in your code, but you are more sure that the compilation flow ends correctly. Okay. So the synthesis process, we already said, HDL language, HDL, Verilog, or mixed. So Vivado, the compiler of AMD FPGA, can work with mixed languages. There is no problem, both for simulation and implementation, synthesis implementation. So the coding technique is what I was saying. So usually we use template code for programming FPGA because the synthesizer has to recognize the hardware structure. Okay, so it's important to be not be very creative in programming FPGA. Then other things that you can use in the code are RTL attribute. So these attributes are a sort of soft constraint that can be embedded in the VHDL language. So what does it mean, soft constraint? It's, for example, there are different kind of memory in my FPGA. In the one that we will see, there are distributed and RAM and block RAM. There are two kinds of memory. We will see the difference. So I can already choose in the VHDL which one of the two to use. So I can leave the compiler the freedom of choosing which is the best for him. Or I can put a soft constraint that says, I would prefer distributed RAM. So why is it soft? Because if it is an attribute, the compiler can say, I'm not able to do it, and I will instead use the block RAM. And he will not raise an error during compilation. It will only give a warning, but it will not stop the compilation. Instead, usually, if you do this kind of things in the constraint, so if it doesn't, it cannot meet the constraint or a constraint is missing, it will raise an error. For the synthesis, the constraint file is optional. So there are very few constraints that are used during synthesis. Let's say some constraint times can help the synthesis process, but usually all the constraints are used in the implementation. So. Okay, after synthesis, we have our circuit that we want to implement. There are few optimization parts that are related to the compiler job, but that are let's say optimization in the power, in the resource needed, in the routing. I mean, there are many optimization, but in any case, the two important parts, three, let's say, are placing. So to decide which resources to use of the FPGA, really which one. So if in your code you instantiate a flip-flop or you infer the use of a flip-flop, in the FPGA there are millions of flip-flop, so we have to choose which one to use for our circuit, and this is the place part. And then there is the routing part, that once you have placed all the part of the circuit, you need to connect them. So this is the routing. There are many paths possible in the FPGA. Not always the short path is the more convenient, because it's a matter of synchronization between the clock path and the data path. So you have to remember that in a synchronous circuit, there are many flip-flop, and all the data is passed by one flip-flop to another, and in the path you need to do probably some Boolean operation, logic operation. But the clock at the flip-flop should arrive almost at the same time. And so we need to account this, the routing of this path, basically. After the routing, we have finally everything. The circuit is mapped and routed, so we can write the configuration memory stream to be loaded in the FPGA. In this bit stream, basically, each bit corresponds to the setting of a routing switch or the setting of a resource to be used. So this is mapped, and this is unfortunately something that is closed by the hardware manufacturer. There are some hardware manufacturers that leave it open, so open FPGA exists. AMD, the big producer, AMD, Intel, Microsemi, are closed. So we don't know how is done the configuration memory. So we can, looking at the bit stream, we cannot say what each bit does in the configuration of the FPGA. There are tools that does the reverse engineering, so with brute force, so changing one bit at a time and see what happens in the configuration of the memory. So this is possible to do, but of course to the bit stream, it's a megabyte, tens of megabytes. So scanning bit by bit, it requires weeks of time. Please.
Sorry, you might have said it already. Could you repeat again what's the difference between placing and routing?
Yes, sure. So placing is to choose which resources in the FPGA you want to use. So for example, I want to use that flip-flop, or I don't know, that block of RAM. And routing is to connect that flip-flop with the following one. So also that is programmable. You can choose different paths in the FPGA. There are routing switches, and then you can create multiple paths.
So one is about the resource allocation, and the other one about the connection.
The connection between resources, exactly.
Thanks.
You're welcome. Please.
How long does this all take? Like, which steps are the heaviest?
Yes. So the heaviest, it's let's say the routing. So placing is also easy, but so synthesis is not easy. It's the fastest. Then we have placing takes time, but most of the time is taken by the routing, because the closing of the timing is done in the routing part. So to calculate each path and close the timing. Because as I said, we have to take into account not only the data path, but also the clock path. The clock path, it's unavoidable that we have a skew in the timing arrival of the clock between flip-flop. So we need to take it into account. It's a double problem. Let's say we have to compensate the delay according to the skew of the data delay according to the skew of the clock. So that's for sure the part that require more time. And then write-to-be stream instead, it's trivial. Once you have everything done. So this is done. This part is done as like a Monte Carlo. You have to find the minimum of your problem. So you give some kick to your function, cost function, to go out of the minimum to a local minimum to find a better minimum, and this requires time. There are also many parameters that you can set up. This is an advanced feature of the compiler to optimize for some, depends on your design. Your design can be resource hungry or routing hungry. So you can tune the parameter of this cost function in order to optimize for resources, for timing. And there are also the possibility in Vivado to use machine learning algorithm for tuning these parameters. So it's quite complicated. If your design doesn't close the timing, 90% of the time is your fault because you make a wrong constraint or you make a code that is not, it's impossible to implement. For example, you need a data path between two flip-flop too long. So you have put too many logic between two flip-flop, too many logical ports, and each of them have a long delay and it doesn't fit. So you need to break this long path. There are techniques we will see, but usually it's your fault. But sorry, I forgot what was to say. Sorry. Anyway, well, okay, sorry. Anyway, this is the most time-hungry part of compilation. Yes, so what I was to say is that it could be your fault, but could be also fault of this algorithm used for finding the best circuit, best routing. So in this case, you can intervene in tuning the parameter of finding the best routing. And you can do it with brute force, and changing, sending several compilation in parallel, with each one with a different set of parameter and seeing which is the best. But this requires days, basically, of compilation at the end. During implementation, we have to take into account also the design constraints, as we said. Mainly, there are three kinds of design constraints. So the physical are the most important. So the pin location, we needed to specify each pin location. Why we needed to specify? Also because of the internal routing, it's important because we needed to know, the compiler has to know where the starting IO block, which starting IO block we want to use and which end IO block we want to use for going out the signal. So this is pin location, and then also as physical we can say the configuration of the IO block, because the FPGA, so as we say, the good part of the FPGA, it's the fact that it's completely reprogrammable, configurable. Also in this part, not only in the location of the FPGA, but also in the logic standard, the electrical standard that the FPGA can implement. So you can interface it with 3.3 CMOS electronic. You can choose this kind of IO. You want TTL, you can design it, you can specify in the constraint file the electrical standards, LVDS, differential signal. So are all electrical standards that you can implement in the FPGA. And this is a programmable part. It is very important, and you have to pay attention to this. Why? Because the FPGA is connected to other components. So the input-output is connected to other components that work at 3.3 volts. Then if you program your output to be 5 volts, you break it, the following component. So the compiler will raise an error if you don't specify the electrical standard, because it cannot infer it. It's very dangerous to do it. So this is a constraint, pin location and electrical standard that you always have to constrain and never leave the compiler to choose it. The constraint can be hard constraint, so I want that part of the circuit. So this is not true only for the I/O, it's all true for every part of your circuit. You can force the mapping to choose a particular resources. So I want to use that flip-flop, not whatever the compiler wants. And I can give absolute constraint or relative. I want to use this flip-flop, and for this other part of the circuit, a closest flip-flop. I don't say which one. I just want to be in the same area, geographical area of the FPGA. This is a relative location constraint. A timing constraint, of course, so I can specify the clock frequency. I can specify for each input and output the delay between the input and my first flip-flop that will start working on this data. I can say it's false path. So there are many constraints on the timing. And power, okay, as power is the constraint that I was telling to you regarding the voltage, but also the current setting. So I can say I want to drive more current for an output pin or less current, depending on if I want to switch fastly that pin or I prefer to save power and change so the switching rate. So this is something that I was telling you. So we have, after implementation, before the bit stream generation, we needed to check that the compiler has met all the timing constraints. So what are these timing constraints actually? So these constraints are basically constrained on the clock period. So I don't know if I can use the blackboard, maybe. Yes. I have to move. So let's assume that here we have a flip-flop and the following flip-flop, it's here. So the flip-flop will receive the clock. And then it has its data in. So usually here, in between, this is the data path. In between, you have logic port, so Boolean operation that you do on the data from one flip-flop to the other. So this is the data path that we are taking into account. So the idea is that this clock arrives at the same time at these two flip-flops. So this is why we need a very good clock distribution in our FPGA. Million of flip-flop, in principle, same time on all of them, so a very equalized distribution net for the clock. So what is the point here? That each flip-flop has some characteristic parameter that are called setup time and hold time. So what are they? So what the flip-flop does? The flip-flop sample the signal. So reproduce the input to the output, send the input to the output when it receives the rising edge of the clock or the falling edge of the clock, depending on how you have set it up. Let's see the rising edge. So at the rising edge of the clock, the data that is here is copied here, okay? If the data changes here, doesn't matter. This will stay as it was until the next rising edge of the clock. This is the behavior of the flip-flop. The flip-flop for working needs to have a setup and hold time. What does it mean? That the data here has to be stable for a while before the rising edge of the clock and for a while after the rising edge of the clock, okay? So this is what we call setup time and hold the time. So we need the data that doesn't change in this part and in this part. So it should be stable, okay? What happens if it changes? It's a mess. The flip-flop doesn't work correctly, and there is an effect that is called the meta-stability. So the output can be whatever, we don't know. It's usually something analog. We will see during the lab part this effect and how to, with the debugger, how to spot this problem. But so the point is that for the correct design, the compiler, the implementer, let's say, has to take into account this. Okay, so your circuit needed to meet the setup and hold time. If the compiler is not able to do it, because, for example, the most common problem is that here you have too much logic. So it's impossible to close the timing. If you have chosen a clock frequency of 200 megahertz, means that this path, data path, is 5 nanoseconds. And here you have 100 logic gate in series, and each logic gate have 100 of picosecond. It's impossible to close the timing for the compiler. So it will say that the setup time is not met, okay? And it will tell you at the end of the compilation. So this is something that you always have to take into account, because if the setup or all the time is not met, means that you need to review your code or your constraint file or your RTL code. Okay, everything is fine, compiled. We can do the bitstream, generate the bitstream. Now we have the bitstream. We have to configure the FPGA. So as I said at the beginning, there are two kinds of FPGA, the static RAM based and the flash based. So we use the static RAM. So what is one of the main difference? Well, one of the main difference is that the static RAM is volatile. It's a volatile memory. It's like the RAM of the PC. So when you power off, you lose the content of your configuration memory. So how to load the configuration a startup? So you need an external device that load the configuration of your FPGA. So during this course, you will use your laptop, you will produce the bitstream, and you will download it in the FPGA. When you power off the FPGA, you lose the configuration, power on, you download again. So that's what you do. But if the FPGA it's deployed in your system, you cannot each time to configure each FPGA by hand. So you need a device that does this for you. So this can be either a microcontroller close to the FPGA mounted in the same board, but this is a costly choice. The other choice that is easier, usually, and less costly, is to use a flash memory that is not volatile, okay? So flash is not volatile, even if you power off the content of the configuration remain, and then at power on, you can download this configuration from the flash to your SRAM-based FPGA. If you use a flash-based FPGA, you don't need this part because it's it's already not volatile. So even if you power off a flash-based FPGA, when you power on, it remains configured. But this is not true with the static RAM. So regardless of which two device we want to use for programming an FPGA, we have to remember which connection are available in the FPGA for programming it. So there is one port that is called the JTAG port that is always available, and is the one that we use with our laptop when we configure it during the course. In the card, there is a bridge, a small bridge, USB to JTAG. So you connect in USB to your laptop, this converted to the JTAG protocol, and the JTAG is used for interfacing to the JTAG port that is always available for also for debugging purposes on your FPGA. But the other two instead port that are available, and usually these ports are available only at power up, so only at start time of the system, are a serial port or a parallel port. This depends on the model of FPGA. So there are some FPGA that are serial configurable, so you send the bit stream 1 bit at a time, or parallel configurable, so you have a bus of 32-bit and you can program it. Of course, parallel is more faster, so you can configure it quicker, the FPGA. Serial, it's more convenient for the routing because you need less wires, less lane. Why we need performance even in configuring the FPGA? Why we want to be fast even in configuring an FPGA? There are some applications where the FPGA needs to be operational immediately after power up. The classical one, it's when the FPGA sits on the PCI Express bus. Why? Because if you put the FPGA in the PCI Express bus of your PC, when you power on the PC, the BIOS starts to scan all the peripherals connected on the PCI Express bus and start the PCI Express scan and enumerate each peripheral. If your FPGA is not configured and so the PCI Express engine that you have downloaded, you have configured in the FPGA is not visible to the PC, it will not find it, and it will just not assign a PCI Express slot to your FPGA. So later, the FPGA, later I'm talking about microsecond probably, but the FPGA will come up and will not, your server will not be able to communicate anymore to the FPGA because it has skipped it during the enumeration phase. So what happened in this case, in this case you need a parallel configuration. So the FPGA has to be configured quickly. Before the BIOS starts, basically. So these are the two ways that I was telling you before. Either use a microprocessor. So in this case, actively, the microprocessor will use the serial or parallel port for the configuring the FPGA and will take the configuration bit stream from an SD card or whatever resource memory that we will be at his disposal. But even in this case, the JTAG port can be always used and it's free to be used. The other case is we use a flash memory. So in this case, directly connected to the FPGA. So in this case, the FPGA at power up, if it is configured for booting with this strategy, will actively retrieve the configuration file from the memory. So at power up, the FPGA will start to provide a clock to the flash memory for downloading the bit stream. So you have to declare basically, so to place your configuration memory in the flash, and the FPGA will retrieve it automatically. It will start from the first address and goes on till it downloaded all the flash memory. So in this case, there is something that if you choose this, that is the more common way to download, and there is also a flash in our board, so we can use this configuration. There is the possibility of doing the indirect programming. So what does it mean, indirect programming? That if we want to update the flash memory content with our new bit stream, we don't have to write it directly on the flash memory. We can pass through the FPGA and program the flash from the FPGA. So the tool provided by the manufacturer of the FPGA allow you to do this downloading of the configuration file to the flash memory. So it will basically, for you, put in the FPGA a special firmware that will do the bridge between JTAG to flash memory. Usually this protocol is SPI, that is a serial protocol for programming flash memory. We will do the JTAG to SPI bridge. Then you download, you copy your bit stream in the flash, and then you ask basically to the FPGA to boot again, to reboot, and the FPGA will take the content of the flash. So this is called indirect programming of the flash memory. There are many other topics regarding configuration. So there are more advanced topics. So there is the dynamic reconfiguration of an FPGA. What does it mean? There are some blocks in the FPGA that allow you to dynamically change it. So, for example, you have a clock generator inside the FPGA, and you dynamically can reconfigure the frequency of this clock generator. So they are blocks that are thought to be with the external port interface that are used for changing some property of them. This is called dynamic reconfiguration. There is the multi-boot option. So in the flash, you can have the possibility of having many bit stream and also switch dynamically between one bit stream and the other. This is very useful when you want to avoid, so the FPGA is buried inside your detector front end, and you don't have possibility of using the JTAG port for accessing it. So it's common to have a golden configuration file, so a golden bit stream downloaded in the flash, and you always start from that one. Then you use a second bit stream downloaded in another area of the flash memory with the actual firmware that you want to use. So what happens when you reconfigure this bit stream? If something goes wrong and you configure it, the second bit stream with a wrong bit stream, something that will break, will stall your FPGA, the FPGA automatically, if it is installed, will jump to the golden bit stream, and you can access to the FPGA again. The last advanced topic in configuration is the partial reconfiguration. So partial reconfiguration means that I don't want to reconfigure the full configuration memory, only some parts. So this is a very advanced topic. So you keep still alive one part of the FPGA. This part of the circuit is still working. I configure only a small part or reconfigure only a small part of the circuit. This happens, for example, for the PCI Express case that I told you before. So I want to be super fast in the configuration of the PCI Express. So I do a small firmware that only configure the PCI Express. So I can download it from Flash very quickly. It's only the PCI Express part. And then after this part went up, I reconfigure all the rest of the FPGA. So I do it in two steps, the configuration. So to be very quick on the PCI Express part. Please.
Like you leave the rest operating as usual and you will configure just one part.
Exactly.
And this setting that you can set it from the bottom.
Yes, yes, yes. Yeah.
Okay.
No, it's a very powerful option for sure. Yes. Yeah. It allows you to have a part of the circuit always running, let's say. And it can be used also for, I mean, let's say for if you have a resource problem, for example, you want to use your FPGA as coprocessor, you implement some instruction that you want to run fast, but you don't have space for all the instructions that you want. Runtime, you can change this instruction while the FPGA is still working and receiving data. But it's, yes, advanced topic, let's say. Please.
So do they have separate clocks, or is it still one clock?
So in the FPGA, you have many clock trees. So there are, I don't know, in this I think that there are up to 32 clock tree. So you can have different tree for time distribution. So you can reconfigure one while you keep the other alive. Usually, yes, I mean, usually the clock is also segmented by region. So let's say that you keep alive one region and you reprogram the buffers of the clock on the others. This is something that can be done. Yes, couple of slides and we are done. Third party, yes, the IP can be, as we said, coming from Xilinx AMD, third party, somebody that wants to sell you some piece of code, can be a colleague that has designed and packaged his code, or very important, because you will also see in the following week, comes from high-level synthesis. So high-level synthesis is a way of programming the FPGA with a more high-level language, so C++ or something similar. It's not really C++ because C++ doesn't have notion of timing, doesn't have notion of parallelism. It's C++ plus pragmas, let's say, plus some constraints that help you to explicitly say the degree of parallelism that you want. So what happens when you use this language? This language will produce VHDL or Verilog. At the end, you always have to pass through this language. Will produce from the C++ VHDL, and it will package this VHDL inside an IP, so you can instantiate as a black box in your Vivado project. A good part of the IP is the out-of-context synthesis. What does it mean? So this is optional. You can choose or not to use the out-of-context synthesis for the IP. So it means that this it's part of a part of your circuit that can be synthesized once for all. So you decide to not change the IP. So you synthesize this part of the circuit, and then you change only your VHDL part. And each time you have to do a modification of your part, you synthesize only your part and keep the synthesis of the IP apart. This is a strategy that speeds up the runtime, of course, because you don't have to resynthesize each time. So it's better, usually. There is a small drawback that the synthesizer cannot optimize the interface between your circuit and the other one, because it's already synthesized. So if you want a really optimization of sparing till the last flip-flop, then you need to disable the out-of-context synthesis. Yes. So simulation. Well, let's make a break and then go ahead with this. Okay, maybe we can resume our lesson. So we were saying about simulation. So we have this three-step possible step of simulation. ERTL, at the netlist after synthesis or after implementation. Of course, the only time accurate is the post-implementation. The post-synthesis is only architecture specific. So we are simulating really the flip-flop, the loot that are there, but not the timing. So which is the simulation flow? So the simulation flow starts from creating a test bench. So let's see what is the test bench in the following slide. So we need an environment that allow us to simulate our design. And we have to write it in VHDL as well. So we need a test bench. Then we need our design that can be just the source file or the generated netlist for the post-implementation or the post-synthesis simulation. And then we can run finally the simulation. So the test bench, it's actually another circuit. So another piece of VHDL that include both our circuit that we want to simulate, that here we call the design under test, so the part of the circuit that we want to test. And there are another two parts of the circuit that we needed to add in this test bench. We needed to add a circuit that generates our input to our design, and we need optionally to generate also a part of the circuit that analyze our output. This is optional in the sense that in any case, the tool will give you a graphical representation of the output of the design. So it could be just enough to look at the waveform of the output of your design. But if you want to check it more carefully and more systematically, you need some piece of code that analyzes also the output. In any case, what is needed, it's the stimuli, so the input. Okay, so the test bench for us, it's basically a VHDL file that collects this part and has no port to the external world because everything is inside a single element. So it's a circuit that has no port, no input and not output, because input and output are generated inside our circuit. So this is the test bench. Finally, a couple of words regarding the debugging phase. So the debugger, it's much powerful with respect to the simulation, of course, because we are spying really what is happening inside of the FPGA, why the FPGA is running, okay? So we can look at each signal, each wire, basically each connection of the FPGA, each output of the flip-flop, we can spy it. So graphically, it's basically the same as the simulation. So our output is still a waveform. So we can see the signal trend in the time. So it's like an oscilloscope. But this is the real behavior. So, and what is the benefit of the debugger with respect to the simulation is not only that is more timing accurate, because it's really execution of the hardware. So for example, the timing, also the temperature of the chip can change the timing. So this is something that in simulation, even if it is a time accurate simulation that is simulating the delay between two flip-flop, it cannot take into account the drift of the delay due to the temperature. So this is more time accurate, and it simulated it doesn't simulate, it actually spy the actual system environment. So I'm looking at the real input to the FPGA and the real output. So many times my system, my circuit is failing because I'm expecting a different input than what there is in reality. So this happens very often. And with the simulation, you will never be able to catch a problem like this. So this is the benefit of the debugger. So what is the drawback? That it's more resource hungry, the debugger, in the sense that you need to instantiate a circuit along with your circuit. So in parallel, you need to put another circuit that is actually the debugger. And this is resource hungry, so it depends also on how much time you want to spy. But for sure, you cannot spy everything. So you have millions of flip-flop, you cannot bring out of the FPGA million of state of your flip-flop with for a long time. So the visibility of the probe that you use for spying is less than simulation. Simulation, you can look at whatever you want without problem. Here you need to choose where to probe in your circuit. And of course, it has a long iteration time with respect to simulation, because the debugger can be implemented as part of your circuit. So you need to go through the full implementation. So till the generation of the bit stream, the downloading, and then you can really see what is happening. If you want to do a modification, for example, you want to spy another signal, you need to recompile everything from scratch. So can be long iteration time. Well, the debugging flow, we will see it. There are two options. So there is a debug, a flow that implements the debugger at the RTL level. So you will put the debugger as part of your circuit. So in the VHDL, you will instantiate the debugger basically. And then there is another flow that actually will insert the debugger at the after synthesis. So after you have synthesized, you have your circuit, and then it will connect the debugger already synthesized, like an IP out of context. Okay. So there is this. We will see what are the pro and contra of this two flow. I think that's enough. So we can move to the architecture of the FPGA. So then, let's say this is the most boring part, probably. So I will not cover the full set of slides. I put it here, there for your reference. We will see it little by little when we will use some part of the FPGA. We will see in detail how this part is done. But so now allow me to skip some slides and let's go only to the interesting part. So then from this afternoon we can start to play with the FPGA and put our hand on. So what are the most important block and hardware block that you find in the FPGA? So here the nomenclature change depending of the FPGA brand, but actually all the FPGA are very, very similar. So the name will change, but the functionality will be the same. So what you are learning today with the Xilinx AMD, it's exactly the same as the Intel Altera FPGA. It's just a different name convention. So what we have, it's using Xilinx convention is CLB, configurable logic block, SM, switching matrix, and IO banks. So these are the bare minimum elements of your circuit. So in the CLB, we have all the circuit element that we need. So flip-flop and logical gate. We will see that they are not exactly logical gate. They are circuits that are equivalent, but they are not logical port like AND or not this port that you will expect. But they are equivalent. So there are a part in the CLB that is used for the Boolean function and a part for the memory, the flip-flop, for the synchronization also. Then there are the switching matrix that allow you to go to another CLB. And finally, there are the IO block that allow you to go inside and outside of the FPGA. Just for giving you an idea of the numbers, so we are talking about 1 million of CLB, and in one CLB there is not only one flip-flop, there are 16, I think, in this family. So a lot of flip-flop, and also thousands of IO. Please.
What are the RAM blocks?
Yes, this is another resources that is apart from that. So you have several other resources we will see. RAM block, FIFO, PLL for the clock generation, phased lock loop. There are IEDC, so we will see most of these resources. They are basically, well, the difference is that usually these are spread all over your silicon. Instead, the RAM block are all concentrated in some area, but yes, they are still accessible through the routing switches. So from a CLB, you can go to the RAM and come back as the same. Yeah.
Also, if you could briefly explain the flip well,
Yes, so the flip-flop, it's an element that is used for mainly in the FPGA is used for synchronization. So you just have to imagine what does the flip-flop does. So let's see if we can erase the blackboard there. So usually you have an input signal and then the output of the flip-flop, and then you have the clock. Then there are other signals we will see, reset, initialization signal of the flip-flop, but these are details. So let's assume this is your input, 0 and 1, so we are talking about digital signal only. Then we have something like a clock, a square waveform. So the flip-flop, it's sensitive on the rising or falling edge of a flip-flop. There are also double data rates flip-flop that are sensitive to both, but usually it's either rising or falling. So let's assume that this is a rising edge flip-flop. So what happened is that your output, it's set at the falling edge of the rising edge of the flip-flop. So here it was 0, okay, again 0. Here goes to 1, okay? So, and stay 1 until the next rising edge, okay? So here is sample as a 0, and so it goes out, it goes down, again, down, and so on, okay? So it's a synchronization stage, basically. So it samples your signal only at a given time. Okay, so this is the behavior of a flip-flop. Yeah, why this is used? It's used because now we can control step by step what our circuit is doing. So we can control exactly what is the logic that is applying between two flip-flop. So the flip-flop, you have to imagine that the first flip-flop is working at the clock cycle, and the following flip-flop, it's at the later clock cycle, one clock cycle after. So when the first flip-flop will act as input to output, then there is one clock cycle for crossing the circuit, the Boolean part of the circuit, and then at the following rising edge, the next flip-flop will do the same. Okay, so that's the idea. Please, there was first year.
So in this schema, so basically I should imagine that each input output is connected
to any CLB. So yeah, here I didn't put the connection, but basically also the IO block are connected to the switching matrix.
Okay, and in schema, so basically the clock will be outside.
Yes, there is another routing that is not so this is important part. So the clock, as we said, it's very delicate part because it has to be distributed with zero skew to all the flip-flop. Skew. So the timing difference between the arrival of the clock to a flip-flop the difference between arrival should be close to 0. because this guarantee the good synchronization of your circuit. So the clock distribution to all the CLB, it's not done with the switching matrix, with the switching block. This is only for data. For clock, there is a parallel distribution and also configurable, but dedicated. So let's say, so it's much more precise, the delay in the routing. So you have to imagine that there are special I/O block for the clock. So you cannot use any of the 1,000 pin of the FPGA. There are some of them that basically allow you to access to the clock tree distribution. So you need to use that pin of the FPGA. They are a gate to go inside the clock distribution that is in parallel.
But a very basic question. For example, if like I didn't understand if the clock should also be distributed to the CLB unit. And in case
yes, because inside there are flip-flop. So you need. So in the CLB, we will see in the next slide, but in the CLB there are lookup table that are the elements that implement the logic port, and then there are the flip-flop after the lookup table. So then also you can skip them actually. So there is a bypass if you want to use only the logic port and not the flip-flop. But usually you use both. So you enter in the CLB with the first element of the CLB as the lookup table. Then you can go to the flip-flop and then you go out of the CLB to the next CLB, where you find another lookup table, another flip-flop, and so on and so forth.
And when I distribute the clock for the CLB, so I'm not sure it makes sense, but for the CLB which are in the inner side, it doesn't take a long time to get the clock there.
Exactly. So the clock is equalized. So if I enter here, and I want to reach this CLB with the clock, I need to go a longer routing before reaching this CLB to equalize for the last, the farthest CLB.
And this is achieved by simply, I don't know, adding a cable or just of the same length?
They introduce some delays artificially in the routing. But this is what I was saying to you, that it's transparent for us because it's the manufacturer of the FPGA that has designed this, and the compiler that he provided to us, Vivado, embed all this functionality of setting properly the delays and so on. If you design your ASIC, then you need to be responsible of the clock distribution tree, and you need to design your own. So. Please.
So I have a question from what you said. I think you said before that these delays between the input and where the data is used, these delays have to be specified by us.
Yes, because so in the sense that the frequency of the clock depends on us. So if here we are using, this is one period of clock, if this is 10 nanosecond, so 100 megahertz or 5 nanosecond, it's our choice. So what is the difference? If we put an aggressive timing, 2 nanosecond, means that from one flip-flop to the other, we can put only very little logic. So not many level of port one after the other, because each port introduces a delay. If instead, on the contrary, we want to relax and use a 10 megahertz clock, then we can do much more things between one clock cycle and the other. So it's a design strategy.
So what we know is the distance between components in clock cycles, because of the difference in logic and output. And then what the manufacturer knows is the distance between components in nanoseconds.
Yes.
And that's what this factor is.
Yes, exactly. So the manufacturer knows the exact delay of each net and the exact delay of each lookup table that we put, so logic port, that we put between the flip-flop. Yes?
So when you were explaining that before the break, I think you mentioned that it might happen that the variations in the input are of finer granularity that the event is.
In the sense that, so what happened, that suppose that here, so usually this should never happen, because what happened is that this should be clocked with the same clock, okay? So this is an asynchronous signal for us. So this input, it's asynchronous because it's not, see, this is asynchronous because it changed only during the rising edge. This is an asynchronous. It's not true that it never happened, but inside the FPGA, never happened because usually you move from one flip-flop to the other. This happens in the input usually. So the input comes from another digital block that is clocked with another clock that is not synchronous. So in the input flip-flop, you can have something like this. But usually inside the FPGA, the flip-flop is just one clock cycle delay, let's say. So you copy the input to the output one clock cycle later. So, yeah, if they don't share the same clock, they behave in this way, yes. So if it's not in phase, or even if they share the same clock, but the two clocks are not in phase, that could happen when you don't, I mean, you don't equalize the timing like is done in the LHC experiment, that there is a system, clock distribution system in all the experiment that is meant for really equalizing the phase of the clock, not only the 40 megahertz frequency. It happens that you have an asynchronous signal, basically. You're welcome. Okay. So now maybe there are many details in this slide. It's an extract, let's say, of the data sheet of the FPGA. So I will just highlight you what is the important part. Then the detail are, I mean, they're less important. So this is what a CLB is. So you have the switch matrix. You can enter, go in and out to the CLB. The CLB, for some reason that Xilinx doesn't tell us, it's built with two slices. It's a sub-unit of the CLB. The slices are equal, so it decided to divide the circuit into two similar parts. What is the difference to have one slide or two slices? So the difference is that these two slices are close together. So the routing, if you want to move from one slice to the other, is short. If you go from one CLB to the other, is a long routing. So that's a detail, doesn't matter. So what I can find inside the slice, that's more important. I can find 6 input lookup table. So lookup table is a way of encoding Boolean function. So it means that here I can find a lookup table, more than one, that has 6 input. So once 6 input lookup table means that I can do a Boolean function with 6 variables. Okay. Then I find the storage elements that are flip-flop. Then I can use this slice also for implementing distributed memory, shift register, and we will see, and multiplexer. Then the other important part is the carry chain. So for implementing sum, so arithmetic, I need a way of fast propagate the carry. So when you do a sum, you need to have a Boolean function between the 2 bits that you want to sum, but also you need to have as input of your function what is called the carry, so the result of the previous bit sum. Okay, so just to, I don't know, I mean, if I'm doing this, okay, this sum, it's like in decimal system, 0 plus 0 is 0, 1 plus 1 is 0, carry 1, okay? So when you do 0 plus 0, you need to have as input also the carry. So this is a 1 and so on and so forth, because it comes from the carry. So you can imagine that this is a sequential way of doing a sum. So the last bit can be ready only when we know this, only when we know this, and only when we know this. So we need the propagation of the carry is the serial part of our algorithm for doing the addition. So having a fast way of propagating the carry means to speed up the sum. So for this, in the FPGA, there is a special part of the circuit inside the slice that take care of the propagation of the carry, and is done with the element with the shortest delay as possible. And then we have a special routing for propagating the delay between one slice and the following one. So this means that let's suppose that this slice has 4 flip-flop, means that can sum up 4 bits, but if I want to sum up 2 number of 8 bits, I need to add another slice, okay? So I need to propagate my carry to the next 4 bits available. So I need a special routing for it. Let's see this element one by one. So lookup table is the way of implementing any Boolean function. How does they work? So you don't have to expect to see the Boolean port here. Actually, you have a structure like this that is a big multiplexer, okay? So you have several input that goes to one output. So this is the structure of a multiplexer. You have other lines that are used for selecting the routing of each multiplexer. So the idea is that, so this is the output of the Boolean function that you want, and these are the input. So this can implement, this structure can implement a 4 input function, 1 output, okay, Boolean function. So depending on the value that you put in these registers, that can be, it's like a memory that you configure at the beginning with the bit stream, so it's the configuration memory. You can put a 0 or a 1 inside here. So a given combination of these 4 lines allow you to select one of these register and put it in the output. So depending on the Boolean function that you want to implement, you choose accordingly the register value, okay? So if all these are zeros, for example, means that you take this one as output. If all of them are 1, you take this one as output and all the 16 cases in the middle. So depending on the value that you put here, you have your corresponding output of the Boolean function. This is the way that in FPGA are implementing any Boolean function. Okay, so in the FPGA that we use, there are, this depends on the family, but all the FPGA are organized like this. In this kind of family, there are 4 LUT each slice, so 8 LUT for a CLB. And there are LUT with 6 input, so bigger than this, and 2 independent output. So there is a possibility of having 2 output per LUT. What happens if you need to have a Boolean function with 8 input? You need to combine 2 LUT. So the output of the first LUT has to go as input, one of the input of the second LUT. This means that you need to concatenate 2 LUT for making a bigger one, and this takes also more delays, but the compiler is taking into account this. Please.
Otherwise, coming after.
Yeah, I mean, so you have a lot of multiplexer. Multiplexer is you have a select line that tell you, I want to copy this line to the output or this line to the output. So it's a 1 bit that tell you this one or this one. Then you have several levels of multiplexing. So in this way, the input can go, so if all of them are configured as 1, you choose this path. If are 0, 1, 1, 1, for example, is this path. Okay, and so on and so forth. So you have 2 to the 4 possible paths. So you have 16 input line that can be copied to the output, depending on these 4 lines. Now, a Boolean function is a function that associates to the input and output. So here we can associate to any possibility of 4 input. So we can build 000, 001, 0010, 0011, all the 16 possibility of the input. We can associate an output depending on how we configure this register. So if we want to implement a function that at all 0 associate a 0, well, we need to put a 0 here. If we want a function that at all zeros put in output a 1, then we need to put a 1 here when we configure it at the beginning of the word, our FPGA. But you don't have to worry about this because all this part is done in the shadow, let's say, by the compiler. You don't have to worry about this. It's very rare that one has to go into this detail, but it's better to know for understanding the function, how to behave an FPGA. LUT and then flip-flop. 8 storage element each slice, so 8 flip-flop. Can be flip-flop, can be latches, doesn't matter, so they are a little bit different. Flip-flop is active on the rising edge of a signal. Latch is active on level of signal. It's a very tiny difference. We don't have to take it into account. What is important is that they are directly connected to the output of the LUT. So from the logic function to the flip-flop. Then there are also other signals. It has input-output clock. Then you have a reset, so a clear enable for clearing the content of the output. And then a set reset signal for setting the initial value of the output of the flip-flop, so before the first rising edge of the clock. Usually, these control signals are common to all the 8 flip-flop. While the data path is different for each flip-flop, the control signals are the same. So if you have a 2-clock design in your FPGA, you cannot mix these 2 clocks in the same CLB, okay? So you need 2 different CLB for if you have 2 clocks. Okay, so these are the lookup table and flip-flop are the only part inside the CLB, but the lookup table can be configured in a special way for implementing something that is not a Boolean function, something that is called a distributed RAM. So we can use the LUT. So if you remember, the LUT has register element, so has memory element. So we can use that memory element, the same memory element, for implementing distributed RAM. So we can use that memory element for storing our signal as a memory. Okay, so we use the LUT for implementing asynchronous RAM with different configuration. So we can choose to have single port RAM, dual port RAM, simple or true dual port RAM. This depends on if basically we want to write in both, we want yes, one port for synchronous write. If you want to have a read-write port or just one write and one read, or quad port RAM. So we have memory that can be accessed with different ports. So this is the schema, but doesn't matter how it's organized. So in this case, basically you have this is the LUT that is configured for being a RAM, a memory, where you have the clock access, you have an address, you have a data. So you write as it's a normal memory, and then you have an output port that can go out of the CLB or can be registered with the flip-flop. So it can be further registered to another flip-flop in output. So there are many configurations that can be used for this kind of distributed RAM. So can be arranged in different configuration depending on the size of the address and the width of the data. Okay, so you can choose. But as you can see, the most important part to understand is that these are very tiny memory. So we are talking about 32 addresses, 128 addresses at most, with data width of only 1 bit. So they are nothing. So they are very, very small memory. The interesting part is they are very small, but they are distributed across all the FPGA. So we can arrange them and concatenate many of them for building our own memory. This is done by the compiler. We don't have to take into account this burden of all the details. But it's good that you know that there is this possibility of using the LUT as memory and not only using the real memory that is available in the FPGA, the block memory, block RAM. Yes. Yes.
I was thinking in terms of, like, for example, the application, which port, like if you could make an example of.
So usually you use dual port to be faster with respect to single port. This is because in a single port you basically have to do in one clock cycle you write in the memory. In the following clock cycle you can make the read. with a dual port, if it is a true, even a simple dual port, you can use, you can pipeline, let's say, and you can do read and write in the same clock cycle. Of course, you don't read the same data that you write, but it's available the following clock cycle. So it's like a pipeline. So one port is writing continuously, the other is reading continuously, one clock cycle before. So all the data. So if you want performance, a dual port is better than a single port for sure.
And the time between the two is dictated by the clock.
Yes.
By the clock frequency.
Yeah. Yes, yes.
And so you can take also the buffer, like you can use this delay as kind of a buffer.
Yes, so you can implement also FIFO. Yes, you can make a FIFO with this memory if you want. But there are other structures in the FPGA. Well, it's so let's say if you want to make a delay, usually you want to delay it for many clock cycles. So yes, you can decide to write on a port at a given time and then read after several clock cycles. Yes, that's also a bufferization that you can do. You can do a FIFO in this way, first in, first out, waiting some clock cycle. Yeah. Please.
Even just about normal computer, usually the RAM requires every some amount of time to refresh the charging RAM. So what if you try to read an address in a normal computer? If you hit a cell memory that is refreshing, you have to have the wait refresh speech. But on FPGA, how is that? You cannot just have the computation, have the FPGA from win out.
There is no this, at least it's not documented, let's say, in this feature. So you don't have this refreshing, or if there is, it's done in a transparent way from the user. So you don't have to take into account this problem. Yes, the memory is still volatile. Yes, yes. Like all the other memories, so it's like the configuration memory. It's volatile. I never heard about this issue in the sense that so the content of the memory is never lost. Then if there are other hardware structures that refresh it, they are faster than what you see, because I never heard about this issue. So the only issue that you have, this is usually it's in the configuration memory. Sometimes you are asked to refresh it because of what is called the single event upset. So you can have, if your FPGA stays in a radiation environment, or for space application, or particle physics, could happen often that you have an FPGA that can be in an environment where there are ionizing particles. In this case, the ionizing particle can change the content of your memory. So it can induce some charge that make what is called the bit flip. So a 0 becomes 1 and vice versa. So in this case, there is a technique that is called scrubbing. So you periodically refresh your configuration memory in order to retrieve the computation to a given state, and not having your electronic stuck in some not foreseen configuration, basically. But this, I only heard about this for the configuration memory, then not for really for the RAM part. Okay, so the same loot can be a memory, so can be also a shift register. So shift register, it's, I don't know if you ever heard about this, it's a structure where you have a concatenation of flip-flop, basically. Okay, so if it is 1 bit shift register, you have several flip-flop connected in this way. Okay, so you make the signal shifting bit by bit, and this can be done in also in the LUT. So in the register of the LUT can be configured for making a chain, basically, of flip-flop. Okay, so in the LUT, here is one slice. Here are the 4 LUT that are inside one slice. There are then multiplexer. Multiplexer are used for concatenating the result of the LUT, and with a select line, you can choose which output of the LUT you want to propagate. So with the 2 level of multiplexer, basically, you can, it's like adding multiplexer to the big multiplexer that you have here. So you can have a 7th bit, an 8th bit function for the Boolean function that you want to implement. So you can have up to 8 input Boolean function in a single slice, thanks to these multiplexers. Then at the output of the multiplexer, you can go out or use the flip-flop. Please.
And then what is the input signal? Is that the selection 7 and
Yes, these are, I mean, it's the compiler that decided to use that. You don't have to take care. So let's assume that here you want a very big LUT with all the 6 input of this, all the 6 input of this, all of this. You need all this input. Then you need also this 3 line for choosing the select of this, and this means a super big Boolean function of 6, 24 plus 3 input. But this is, I mean, you code the Boolean function, the compiler decide how to assign your function, your variable, to the input of this big LUT.
yeah. Then what is static and which part is going?
So so this part is static. The register is the configuration memory, basically, and this is dynamic. So the select is dynamic. Yes, the same as for the multiplex. Yes, the select is dynamic. So these lines that configure this are dynamic. Yes.
And also what was the register? That was a flip-flop, right? Yes,
this is the flip-flop that you can instantiate at the end of the LUT. Can be one like this. Here you have only one output of this big LUT, but actually you can have 4 output, and so 4 flip-flop, or even each LUT can have 2 outputs independent for implementing more than 1 output function. So you can have up to 8 flip-flop directly connected to each LUT, basically. So this is a possibility to.
Why do you want this flip-flop there?
So it depends. So this depends if you want. I mean, depends on your logical function that you want to implement. It's up to the compiler to decide if the logical function is very small. If it is able to implement in only one LUT, then you want to use your dedicated flip-flop, and having the other LUT for another function with its dedicated flip-flop, even to part of the circuit that is very far from them. So the compiler can choose to map it in a single slice. Doesn't matter. I mean, if usually not the case, but it has the freedom of breaking the logic in several LUT, or if it's needed, to combine all of them in a single function. So it's up to the compiler, completely transparent from our programming. So where are the input? So I don't get to the question. What there is written. They can be combined in a bigger multiplexer up to a 16:1. So it means that you have 16 input that can go to this basically output. So you have 4. So why 4 and not 6? Because 4 data and 2 are the select that you need for the multiplexer inside the slice. So if the LUT is configured for being a 4:1, means that for 4 for 4 input you need 2 select line. 2 to the second, it's 4. So for choosing among 4 lines, you need 2 select lines. So 6 in total. So this means that you have 4 input multiplexer for each LUT, and the 2 extra input are reserved for the select of this multiplexer. So yes. So this is the symbol of a multiplexer. Let's assume that this is a 4 input. So what we need, it's basically to decide this connection, which one. Okay, so we want to select which line to connect to the output. So here we have 4 possibilities. So we need to decide with the 2 lines which one to choose. So if these 2 lines are, for example, 0, 0, we assign this input to this output. 0, 1, 1, 0, 1, 1. Okay, so this is the behavior of the multiplexer. So if you need the 16 input multiplexer, then 4 lines of select line are needed, because we need to go up of 16 cases, 2 to the 4. Okay. Please. So actually, if the input of our Boolean function are the select line, actually. So with the select line, we choose the output that we want to put, the register that we want to put in output of our function. So our variable of the Boolean function. So let's assume that here you want to do a Boolean function that y output, it's equal to a, b plus cd. Okay, I want this Boolean function. This is OR and AND port. So in Boolean, when I put a plus, it's an OR. Dot product, it's an AND. So this is A and B, or C and D, okay? I want to do this Boolean function. Well, I need to connect A, B, C, D to the select. And then let's do the example. If all of them are zeros, 0 times 0 plus 0 times 0 is 0. So it means that in the register corresponding to all zeros, I need to put a 0, because when all of them are zeros, I want that in output I get a 0. So if all of them are zeros, all the switches, all the multiplexer point to this first register. So in this first register, I would put a 0. If, for example, they are A, it's 1, B, it's 1, C, 0, and 0. So this is 1 times 1 is 1 plus 0. The output is 1, okay? So I want that Y is 1 when the input are 1, 1, 0, 0. So I go here, 1, 1, 0, 0 means 0, 0, 1, 1. In this register, I have to put a 1 because I want, with this particular combination, that my output is 1. Okay, so in this way, I build, the compiler build the register state, the initial register state, and then in my execution of the code, I change A, B, C. So these are my variables. Okay. Last element that you find in the CLB is what I was saying before, the carry logic. Okay, so this is it's an element that is between the LUT and the flip-flop. It's a chain of for the carry. So the carry that comes from the computation, the sum done in the first LUT, is being propagated to the output of the second LUT. So you have to imagine that this LUT is doing the sum of 2 bits, this LUT the sum of 2 bits, and so on and so forth. So one slice you can do the sum of up to 4-bit number. The carry has to propagate and be computed in the following bit, let's say. Okay, so it doesn't matter the detail. So the idea is that this is a way of so what would have been the alternative if I don't have at my disposal a carry chain? How can I do a sum? Well, it's still possible to have this output, the carry in output of this bit, going into the LUT. Okay, so going out of this LUT and coming back to as I can add it as a new variable, an extra variable of my sum computation of this bit. But this required time to go out and then come in again. So the producer of the FPGA has designed this small logic that adds the carry to the computation of the sum of the next bit, just to be faster. Okay. Okay. Very quickly. So what is all the things that I tell you till now are true for the 7 series FPGA. That is the one that we use it. So this is a quite old, well, it's not old, but it's not the newest. So there is another 2 family newer than this, the ultra-scale FPGA and the Versal, the latest. So what's the difference? First of all, the difference is in the silicon. So the process of built in the silicon. We have the channel of the transistor width that is different. This is a 28 nanometer. Ultra scale can go up to 16 nanometer. Versal, newest FPGA, 7 nanometer, so faster. So they allow you a clock speed, a faster clock speed, because the switching rate of the transistor, it's faster. But architecturally, so these are difference at the electronic level, but architecturally, what are the difference? The difference are very few. So whatever you learn from a family, you can extend clearly, easily for the others. Here I just pointed out in this slide what are the difference between the 7 series and the ultra scale series are only details, basically. So number of elements in a carry chain, instead of 4, they are 8, number of flip-flop or independent clock line. So all these are small details. The architecture never changed. And this is true also for Versal. This is true also for Intel Stratix FPGA. So they are very, very similar. So, but also Microsemi, even if they are flash-based, the architecture is the same. So what you learn from one, it's easily to extend for the other. Okay, I will skip the clock distribution. We will talk it later when there is the need. And yes, maybe we can also, well, let's review this, and then so we finished for today with this boring part. As I said, there are other elements up to the CLB. So these are not inside the CLB. These are hardware elements that are still connecting to the switching matrix. And one classical one is the block RAM. So in all the FPGA, you can find the block RAM. So as you can see immediately, the size of the block RAM is completely different from the distributed RAM. Here we have 36 kilobits of memory, quite, I mean, if you are comparing with the CPU, clearly there is no way of comparing it because the size is completely different. But you have to imagine that these are fast memory, so it's like a register for the CPU, not the memory of the CPU. So this memory is very close to the computational unit, so you can access it much more in a faster way. So even this memory can be configured as simple or dual through port. They can have they are very similar to the distributed RAM because they have also output flip-flop, so they can be synchronous, and they are just bigger. And also there is the possibility of cascading them, so you can concatenate more memory for having bigger memory. So at the end, in an FPGA, from kilobit you can reach megabits, basically concatenating all the block RAM. There are also built-in FIFO, so special memory configured as being a FIFO. So simple FIFO, one port for writing, one port for reading. These are very useful because the port, as in the memory, can be configured with a different clock. So you can clock write in the memory or in the FIFO with one clock and read with another one. This is very convenient, the FIFO used in this way, for changing clock domain. So if I have a part of the circuit that works with one clock and has to exchange data with another part of the circuit with a different clock, faster, slower, doesn't matter, but different, then I can put the FIFO for disentangle the two parts of the circuit. So this is a way of making a cross-domain clock in hardware. Very important piece of hardware that is not in the CLB, but is so used in an FPGA, it's what is called DSP, Digital Signal Processor. So you have, maybe you have heard about this regarding the implementation of neural network in an FPGA, because this is the element that allow you to do the multiplication. So without DSP, making multiplication in LUT, it's of course possible, but it requires a lot of LUT. So here you have a dedicated component that does multiplication. Not only multiplication, it does also the accumulation. So what is also needed in machine learning. So it has, the core is the multiplier. So in this family, the multiplier is a 25 times 8-bit, 18-bit multiplier. So it can multiply two numbers, one up to 25-bit and the other up to 18. It has a pre-adder, so you can have the possibility of making addition between two inputs before the multiplication. But the most interesting part is the accumulator after the multiplication. So you can do the sum of the output with the next multiplication. So this is the MAC that are used in all the network, basically. This is a configurable element, so you can do the accumulation with an add, you can use a subtraction as a sort of accumulator, you can do Boolean function in the accumulator. So what is important is that you have an internal feedback path that is delayed. This is the symbol of a flip-flop. When you find this arrow, means that this is delayed by one clock cycle. So the output of the adder is delayed and then sum up to the next clock cycle multiplication. So this is an important element. If you want, also this is an element that can be concatenated. So for example, this is 8-bit, can do multiplication 25 times 18, but if you have two number of 32-bit, you need to concatenate to DSP for making the multiplication. And all the DSP are connected to the switching matrix, so you can access it from the CLB. These elements are, how many there are, depend on the size of the FPGA, in order of thousands or 10 of thousands. And they are completely parallel, so they do multiplication completely in a parallel way. In the FPGA, you can find also microprocessors. So there are two ways of having a microprocessor inside of the FPGA. So there is the possibility of having a hardcore microprocessor. So like in FPGA, like the Zinc. Zinc, it's a sort of 7 series FPGA like this, plus an ARM Cortex processor, interfaced with the logic part, interfaced with the CLB, with the I/O of the FPGA. So you can have a special interface between the processor and the FPGA. In this case, you need to use different programming environment for the logic part and your C++ or program that runs on the, or Python that run on the ARM Cortex, and then you need to interface the two. There is another possibility in the FPGA that is to use also soft core processor. So what is the difference? So in the first case, the processor is really hardware, so it's a piece of silicon like the one that you have in your PC. It's exactly the same, just included in the same chip of the FPGA. In the second case, you are using the CLB, so the LUT and the flip-flop, for making a CPU. So it's it's a CPU built with configurable part of the circuit. So there are many free available free designs, so you don't have to write your own CPU. You can buy it or get it from open source project. Of course, it's less performant because it's not an hardware built for doing this. You are using the configurable part, so you are limited to the FPGA clock, hundreds of megahertz, while in the Cortex you can go up to gigahertz. And but you can imagine that how you can massively parallelize your CPU. So you can make arrays of hundreds of RISC-V processor in the same chip. So and you can connect the input-output of your processor in the fashion that you want. So you are free to use your computation unit as you prefer. IO resources we can skip because we will see it in detail later. Last element that you find in the FPGA, well, in this series of FPGA, it's an analog to digital converter. It's nothing special, but can be useful if you need to be interfaced with analog signal. The FPGA is completely digital, of course, as all the elements are digital. So if you need to read an analog signal, you have to digitize it before. There is a digitizer integrated in the FPGA. It's not a very performant ADC. It's just 1 mega sample, 12-bit, but it's very practical if you want to, for example, to read the temperature sensor or to see the status of your power supply of the board, to see if the level of the output of the power supply are okay. So it has a lot of input, and it's able to multiplex this 1 mega sample to all the 16 input of the multiplexer of the ADC. So it's able to read one by one serially all the input signal, all the analog input signal. So this block, it's always available in the FPGA, and even if you don't instantiate it in your code, it's working. It's always on, because actually it's reading a temperature probe that is inside of the FPGA. So it's needed by the control of the FPGA to understand if you are running over temperature and switching off the FPGA in case. And also it's reading all the input powers of the FPGA to check that everything is fine. So this, and you with the programming tool, you can read this value actually. Very easy, you can see the plot of temperature. So this part is always working. Then if you want to use all the other analog input, you have to instantiate this block as an IP in your code. Okay, so I think this and this set of slides. So if we have 5 minutes, so I would propose to check if Vivado is working. So this afternoon we can directly start to, well, I will show you some, as a tutorial, some example, but if you want, you can do the same things in your laptop. So I think that you need turn on the laptop, yes, and open a terminal.
So we installed two versions.
Yes,
Remember which one is
the 2024.2. So
open the laptop, there should be open a terminal.
OPT, yes. This should be, you need to find Vivado. (2024.2). And then there is a file that is called settings. So you need to source that file.
I don't know where he's gone.
Should be the one sh setting 64.sh. Yes, should be without. Yeah. And now you can write Vivado and should start. Let's see. Works. Okay.
Combination of some of the pieces and also highlighted with so here the MacBook is like option. Yes,
So then, after running Vivado, you should find a screen like this. So after sourcing, type Vivado, and you should end up.
Stuff like this, I really have no idea what this is. I guess if you oh yeah, it's really nice. You can click on the you can click on the learn the way I learn or something. Yeah, that might be helpful. You can also ask it directly. Yeah.
Okay. Welcome back. Not sure I shared the screen with Zoom, but in case somebody will complain, I think so. So you see you hear an echo? Okay, I'm not mastering very well the connection here, so let's hope everything is fine. So let's come back to now to the practical implementation of VHDL in FPGA. Let's start with a super easy example. It's super easy, but it's complete. So we will try to implement a single logic port and make a full project with just one logic port till the end, till the implementation in the FPGA, and verify that it's work. So this is useful also to verify that your setup it's correctly configured and you are able to arrive till the end to the generation of the bit stream and to deploy also the bit stream on the FPGA. So just a couple of comments before starting. Well, we already talked about this morning. Actually, just to repeat quickly, this VHDL, it's used for representing a digital circuit. So we have to understand that what we program, our code, will be translated in a digital circuit. It's not meant for execution. Well, it's the digital circuit that will execute, actually. So let's start to the basic notion of VHDL. So in the VHDL code is divided into two main environments. One is called entity and the other is called architecture. So in the first, in the entity, you describe the port that your circuit will have. So the interface of your circuit. You will describe the input and output of the circuit. So in this example, where we want to describe a Boolean AND port, we give a name of the entity, and then we declare that we want to use as port two signal X and Y that are input for our circuit, and this is the type. So they are type bit. So bit is a type built in VHDL, and it's a type that can assume only two values, 0 and 1. Then we have a Z that is an output, always type bit. Okay. With this and the entity, we close the environment entity, so the declaration of our input-output. The other block is the block called architecture. So the architecture describes what the circuit should do. So in this case, we have starting keyword is architecture. We give a name of architecture, and we refer to the name of the entity. This is because actually we can have multiple architecture for the same entity. So we can, this is allowed in VHDL, pretty much never used, because usually you have one entity, one architecture. But there could be cases where maybe you want an architecture for the synthesis and a different architecture for the simulation. This also could happen. Usually you have a single architecture. The reason why you can have multiple code for synthesis and simulation, it's because VHDL language used for synthesis is a subset of the VHDL, the full VHDL. So in simulation, you can use constructs that are not allowed in synthesis. Why? Yes. For simplicity, because in the simulation we want to use the stimuli, we want to describe the stimuli, and there we don't want actually to build hardware starting from that stimuli. They are used only for the simulation. So for simplicity, we use constructs that are more complicated and that actually the synthesizer is not able to convert in hardware, but we don't care because we will never convert it in hardware. Sure.
talking now about the next bench?
No. We are talking, yes, actually, yes. So in the test bench, you can put some instruction that are not synthesizable. Yes, that's the point. So for example, wait statement. If you want to set a signal and then wait for some nanosecond and set another signal, that a wait statement is not synthesizable in VHDL. So for this, you need to add a flip-flop that, or a shift register, like a chain of flip-flop for delaying your signal. Instead, in simulation, you can say, wait 3 clock cycle, and that's it. You don't have to describe the circuit. In this case, we give a name to this architecture, example 1, refer to entity and 2. Then we have a keyword that is begin. So in this case, so there is part of the code before and part after the begin. So before the begin, we have to use all declare all the internal component of our circuit that we want to use. In this case, we don't have internal signal. It's super simple. We will see later what does it mean, the declaration of the internal component. For the moment, we use the keyword begin, and here we start the description of our architecture. So this is the operator for assignment, like equal in C++. For checking the equal in operator in C++, the equivalent is the simple equal in VHDL. The assignment is an arrow instead. So here we have the Z port is assigned with the value X, and the operator, it's a built-in operator in VHDL, Y, okay? Very, very simple. End of the architecture environment. This is an example, that is what we are going to deploy. I give here you another example, much more convoluted way of describing the same architecture. So like in software, that you can code differently the same things. Also in VHDL, it's possible to use a much more creative way of doing the same thing. So in this case, I create another architecture, example 2. I assign to Z bit at high level 1 when this is a sort of, we will see later, but okay, so this is a sort of if. Okay, so if the concatenation, this is the concatenation operator between X and Y, so we are taking the 2 bit, we are putting together to form a bit vector of 2 bit. When this bit vector has the value 1, 1, then assign 1 to Z. Otherwise, assign 0. Okay? It's please.
So the bits are string. So I shouldn't write one edge 1, but one.
Yes. So this is a complication in VHDL. If you use 1 bit, you need to put one single, what is the name, accent or whatever, this symbol. Instead, you need 2 if it is a concatenation of bit. So if it's only 1 bit, you need 1 quote, single quote, how to call it, and the double quote instead if it is more than 1 bit. Yes, they are declared as single bit. Yes, the % is a concatenation of the 2.
In the end, is another way to say and, like.
No. This AND doesn't have nothing to do with this AND. So this is the Boolean operator. This is the concatenation operator. So from 2 bit, I made a bit vector of 2 elements. So let's say how to say. So you can create a vector of bit in VHDL. So this is a 4-bit vector, for example. So each vector has an address. This is a 5-bit vector. So, and the vector has a content. So I don't know, I put it randomly. Okay. So this is a vector of 5-bit where address 0 has content 1, address 1 content 0, address 2 content 1. So if you want, if this vector is called A, this is a bit vector, 5-bit, so A0 correspond to value 1, A1 correspond to value 0, okay? So this is basically the concatenation of single bit. So A0 as data type bit, the full A, this is A0, the full A has data type bit vector. Zero, 2, 4. We have to say also the dimension, okay? That's Of course, nobody. Please.
So one of these entities, like what piece of the architecture is this now describing?
Yes. So no, sorry, I didn't understand the question. So this is the entity, the envelope, so the port, and the architecture is what you do inside your module.
Okay. So I meant that with architecture, I meant what we looked at in the morning. So
no. Then we will see what the synthesizer will understand and what with component we will use. Okay. Actually, as we see, I can anticipate this. As we have seen this morning, there are no logical port inside the FPGA. So the only way of implementing an end port is using a LUT. We will see this.
Sorry,
please.
Last question, just to understand if I understood that. So if we want to use this
double quote is when we want to represent more than 1 bit.
So in this case, for example, in case of the A vector, it would be double quote like 1, 0, 1, 1, 1.
Yes, we can do something like this. Yes, we can do this. So A assigned. Okay, yes, and 1, 1, 0. Dot. This is the end for the assignment. Yes. The reason why there is this difference, it's I don't know honestly why you need a different symbol for single or multiple bit. Please.
Yes. When do you split your program into and the bits? Like similar to functions in
Yes, so the notion of function there is also in VHDL. Let's say that so there is a keyword, an environment that is really what you think is a function, but instead the idea of function that is translated in a circuit is I describe a part of the circuit that I want to reuse many times. So this is the what is really a function in VHDL basically, and we will see in a while how to use it, how to generate multiple times the same circuit and connect together. Yeah, we will arrive to this. There is also, and it's something that you do inside of the architecture, basically.
Yeah, would your program just have one architecture, or?
Yes, so you need to have to synthesize only one architecture. Even if in the VHDL file you can put as many as architecture you want, it's allowed, but you need to declare one for the synthesis. You cannot synthesize multiple architecture. Okay, so these are two architecture. I put it as just an example, just to say that they are equivalent. So they will synthesize in the same way, even if this is, of course, nobody will use this way of describing. I mean, it's an overkilling for an end port, but logically they are equivalent. Okay, so let's do a little step forward. So here I told you that the type is bit. It's true. This is the default type, the built-in type of VHDL, but it's a type that is never used, actually. Bit and bit vector. Why is never used? Because in the reality, there are not only two values that a signal can have. So 0 and 1, it's a bit reductive, let's say. So you have much more type that in hardware can be, that the hardware can have. So these are actually the standard logic type. So standard logic is the most used data type. Unfortunately, it's not a built-in data type in the language, so you need to declare a library for using it, but it's mandatory to use it. Otherwise, the compiler will not implement it correctly. So standard logic means all this value. So we have a value U for uninitialized, so means that your flip-flop, let's say, the output of the flip-flop has never given a value. So it's before the value before the reset. Then we have an X that is used for conflict. So what does it mean? That if I have two lines that want to drive the same signal, and one is 1 and one is 0, it results in an X. So then we have 0 and 1. We have Z. So Z is high impedance. So the hardware the output of an hardware block can be placed in high impedance. Means I'm not driving this line. I'm using this line floating, not floating, high impedance actually. So I'm putting this line in a state that doesn't hurt the communication between other drivers. So in a bus, for example, when you have multiple driver connected, you can have only one driver at a time, because otherwise you create X conflict between the data. So you put one driver to Z and the other can take the lead and start communication. So then there are WL, so these are data types that are less used, but still exist in VHDL in the standard logic library. So these are basically weak 0, weak 1 are used for the pull-up. So in electronic, you can have, at the electrical level, you can have a driver that actually drives the line, and the line can have a pull-up or a pull-down, okay, in the circuit. So this is a way of having like a default value of the line. So if you have a pull-up like this stay logically at 1, even if the driver is not doing anything. So this is actually a weak 1, it's called, because if this drive it to 0, then it becomes a 0, even if there is a pull-up. Okay, it's stronger. The driver is stronger than the pull-up. So these are tiny difference that, well, you probably not use. You will never use this pull-up, but they are foreseen in the standard. What you will use is the first 5 elements. Well, you never place the X directly on, you will never assign an X to a signal, but the simulator can say to you, pay attention that this line went to X. Please.
There are differences in the lines like pull up and pull down directly to the FPGA, or is it better sometimes to have them resistor placed like in the PCB?
So first of all, we have to say that pull down are only in the I/O block. So internally of the FPGA, there is no need. Then yes, in the I/O block, you can have it internal or external. So I don't think that there is a special. I mean, the advantage of having internal is that you spare component. You can be more compact in your design. Imagine to have 1,000 of I/O means 1,000 of resistor pull up, 1,000 of resistor pull down. So having internal, it's a spare of space. Every input, yes, even input output has both a pull up, pull down resistance, also a series resistance that can be tuned for adapting the matching impedance. There are many things inside the I/O block that can be tuned, and it's every input and output. And in the constraint file, you can set it to them. Please.
Why the don't care does exist? I mean, if I don't care, it means that the signal is not bringing any information.
Yes.
If it doesn't bring any information, why do I need?
Yes. Yeah, I think that is just for simulation. So okay. If for checking condition in simulation, it's okay. You give this value for saying that you don't care of a particular state. So it's not synthesizable. Yeah, you're welcome. Okay, so coming back to our simple code, if we want to make it real, we need to declare the library for the standard logic vector. So this is the statement for declaring the use of a library, like import in Python. And then you say that inside this library, you want to use the standard logic part of the library. Okay, so this is come before everything, then comes the entity. Now I changed it. It's not anymore bit vector, but standard logic. As for the bit vector, there is also standard logic and standard logic vector if you want more than 1 bit. Okay. For the rest, we can keep this and try to implement this simple code in the FPGA. So what is the FPGA that we have at our disposal? It's an RT7, so the series is called the 7 series of AMD Xilinx. RT, Kintex, Virtex are all model of this family, and the difference is mainly on the resources that are inside. So RT is the smaller, Kintex medium, and the Virtex the biggest. So the first, in blue, you find the first line, the part number of this FPGA. There are 2 types. One is XC7A, that means RTX7, basically. Then you have 100. This 100 is tell you how many CLB there are inside. So there are 2 kind of FPGA. Here we have the 100 and the 35. So 35 is a little bit smaller. So depending on which one you pick up, you need to declare this in the project setting. We will see how to do it. So these are for reference, just few value of the resources that there are inside this 100. There are 15,000 slides and 4 megabit of block RAM. 6 CMT are the block for generating the clock, basically. So you can have up to 6 generator of clock. 240 DSP. It's a small FPGA. So these are the part I highlighted the part that we will use. So we have buttons, push buttons, this one. 4 push buttons, 4 switches, so that can have 2 value. Then we have 4 LED, green LED, and 4 RGB LED. So RGB LED are LED that can have 3 colors, basically, and you can also combine the colors together. So you can have multiple color on the same LED. Then what else there is important? There is another push button that is actually very similar to this one. It's red, so usually you use it for reset purpose, but actually is another line towards the FPGA. So it has the same meaning of this. It's not that it's really resetting the FPGA. It's just a line that you will have to use as a reset. Then what else? This is the the USB to JTAG bridge. Okay, it's the one that we will use for configuring the FPGA. It has also other functionality. It can be also a bridge between USB and UART. We will see later what is used for. Okay, here I put the link for the reference manual, constraint file. So this is the master constraint file that the hardware producer gave us, so we can use it. It tells us basically which is the location of the pin corresponding to each of the hardware in the board. So if I want to use button 0, I go in the constraint file and use the line corresponding to button 0, and this line associate the pin of the FPGA used for button 0. It will add it to my constraint file. It will add the location of this pin. So we will see immediately how to use it. And also we are going to see how to build your own constraint file in case the hardware is not it doesn't come with the constraint file. That is happen very frequently. The other important documentation is the schematics. This you must have it, otherwise you cannot do your own constraint if you don't know where the lines are connected. So I give you an example of minimal constraint file for this end port. So at least we need the pin assignment. So we need to say 2 things: which pin we want to use and the electric standard. So we have 3 ports, so we need 2 constraints for each port. We need the port X, Y, and Z. So this is the output and the 2 input. So here we need to make the association between location of the pin and the port of our design. So how to choose the correct pin? We have to look at the schematic. Here I cut and paste the part of the schematic that we need. So I want to map, for example, the 2 input to 2 of this switch. And I want to map the output of my end to a LED, so I can see the value of the output. So for the input, I choose switch 0 and switch 1. So you can see from the schematic that are these 2 switches that connect either the line either to ground or to 3.3, so high value. Okay. So this line if I follow in the schematic, goes inside my FPGA XC7A100T, okay? Where in pin A8 for switch 0 and in pin C11 for switch 1. So what I put, it's a constraint that set the property package pin for port X to A8, for port Y to C11. And then, as electrical standard, I use LVCMOS 33. Why this? Well, we have to read the documentation. It should be written clearly in the documentation. Otherwise, you need to look at, well, you know that this is a 3.3 logic. And so usually in the documentation also tell you if the line has particular termination or is directly connected to FPGA. Like in this case, you can use the LVCMOS. In the master constraint file, you find the same thing already placed for you. For the output, Z, well, sorry, we have to look at the LED that we want to use. Let's suppose that we want to use LED 4, one of these. So LED 4, it's connected to pin H5. So same as before, I put H5 in the connection constraint. Okay. So let's start Vivado and let's try to do this simple project. So I will do it. If you want, you can do it in parallel. So this should be the interface that you find when you do the settings of, sorry, the source of the settings, and then you launch Vivado. So you can start with the create project. Next. So here you give a name of the project. I don't know, we can call it hello, or whatever you want. So it will build, so this is the location of the project. He will build a folder, a subfolder inside of the location. So in this case, the root is project, so you will build a hello world inside project. So probably I already have this, so let's call it LOW. So the kind of project is RTL, the one that we will always use it. So we will only program at RTL level in this example. So now you have a choice. Either, so first of all, make sure that here you have HDL and not Verilog as target language. And for the simulator, language can be mixed, doesn't matter. Here you have the choice of either adding file, if you already have it, some HDL file, or create a new one. So for this time, we will create a new file. So we have to choose the file name. So we can call it and2, like in the example. Okay, then we can go ahead with the next. So same interface for the constraint file now. So either we add, either we create. So let's create a new one. We call it pins, for example. We have just to declare the pin name. Yes, please. Sorry? RTL, the first one, yes, the default option. So this is the default extension for the constraint file. It's a .xdc. It's the default extension of the constraint file. It's let's say it indicates the language for constraint used by AMD. If you change manufacturer, probably the extension is different. That's I can try. Just a second. Yes, I will try. Well, the font it's only for the text editor inside Vivado. Instead, no, here I need the operating system to rescale.
On Windows there is a software called Magnify.
Ah, yes, yes, also. Let's try. Yes. Thanks. I think it didn't work. Okay. Okay, here we are. Okay, but so this is the RTL. Then you can create file, put a name of the file, then it will display here. So here you can create, put a name, and then press OK. So he should add it. Then I will remove this, otherwise. So here you can choose synthesis simulation, it's fine. You're using both. And then next, so same thing for the constraint file. You create a file, pins for example. It should display here. Okay, now here we need to choose the part number of our FPGA. So first of all, take an FPGA. Otherwise, so one every 2 students. Yes, exactly. It cannot be sold anymore. Yes. Yes, sure.
I wanted to go.
So yeah, here you can have so yeah, you can choose the board, yes, or the part. So usually I go to the Arctic 7. So this filter out some part. So if you look, this is the package of our speed grade is the -1. So if you want, I can tell you what are this option. So in the your part number should be this one or this one, depending on which FPGA you have. So if there is no sticker on the FPGA, is at 35. If there is a sticker, is the 100. Okay. So the part number is composed by this part. So the first 4 letters are the family. Then there is the package. Okay, CSG324. It's the package type. Then there is this -1 is the speed grade. What does it mean, the speed grade? It means that so the FPGA are chip produced in a buffer, like all the chip. So the region of the buffer are not all the same. So there are the inner part of the buffer has a better dopant distribution than the region in the outer border. So the manufacturer will qualify after production each FPGA and mark them as speed grade 1, 2, or 3. Speed grade 1 is the less performant, so the one that can go at the maximum clock speed lower. So basically, speed grade -3 is the more performant, and they sell it to you at a different cost, of course. So these are speed grade -1, so the peripheral of the buffer. And that's it. So then you can choose between the 35 or 100. So the size, you can see that the resources changed from 63,000 LUT to 20 LUT. Okay. The L is for low power. So, yeah, low power. Yes, it's more or less the same. It's only used for the calculation of the power at the end of the report. So the low power, it's exactly the same FPGA, but powered at a lower voltage, the core of the FPGA. Okay, in my case it's the 35. So I go next. And that's it. So here we can finish. So here it's a wizard that helps you to define the port of your VHDL file that you have created. We don't need it. We will do it manually. So let's press OK like it is. He will complain. I'm sure. Yes, that's it. So now I'm sorry that it's a bit big. So let's see this dashboard how is divided. So on the left side you have the flow navigator. So here we have the setting of our project, so we can change the setting that we have just set. We can add new resources, new VHDL file, new constraint. We have language template that help us to define if we don't remember the syntax or so on. We have the IP catalog. This is used if you want to implement an IP, to put in your code an IP that is already provided by AMD. So here you can find all of them. If you have a third-party IP as the same, you can add it to the IP catalog and you will find it there. IP integrator, we will see later if we have time what is used for, but for the moment we can go to the other option. So we have the simulation. Also this we will see later how to simulate your design. For this simple end, let's skip it. Then we have this will do an analysis of your code. It will spot if there are syntax error. It will tell you what he understood by just looking the VHDL of your code. We will see how to use it. Then there is the synthesis, the implementation, so all the steps that we have seen. And finally, there is also the generation bit stream. So here are the steps that we can launch one by one or all together. We will see how in a while. Here you have basically the hierarchy of your design. So this you have all the design sources. In this case, we only have one file, so very easy. If you have multiple files, could be that you find it concatenated one inside the other. We will see also this in a while. What does it mean to have a hierarchy? It's the sort of function that we were talking before. You have also the constraint file. We have one constraint file that is now empty. Okay, we have to build it. Simulation sources. We have we don't have a test bench. We have only our design inside of the simulation sources. We will see later. Okay, here you have a tab for the property of the file that you select. So it doesn't matter for the moment. Let's go to more interesting part. Here you have the result of the synthesis, result of the implementation. When you will launch them, here you will see the timing. If you have timing issue, it will appear here. I will talk more in detail on this later. And also you will have all the resources needed by your design. And also you will see how many times it has taken to run the synthesis and the implementation. In this panel, you can use it as text editor. So you can, I'm sorry that with this level of zoom, everything is very, very small. Doesn't work. let's try. I'm not able to. Okay. Maybe now it's too large. Well, we can use only this. Okay. So let's have a look of the file that it has created. So at the beginning, so the minus minus is a comment in HDL, so you can skip all this part. So we can find it has put it by default. Sorry, it has put it by default the standard logic library that comes in the IEEE package. It's proposing to you to use also a numeric library that is used for arithmetic. We will see it later. So you have just to uncomment it if you want to use it. And also it proposes you to use a library that is a library of the primitive of the Xilinx FPGA. So here you find, if you want to use some basic building block of the FPGA, and also this we will use it later. Let's come to our entity. So this is the part that we have seen. So actually here we have to put our port, like we have seen in the slide. So here you have an input. Sorry, this is the compiler. Okay.
Yes.
Okay. So this is the declaration. I think in the you can put also if the two ports are exactly the same direction and the same type, you can put also x comma y or put it in two different row. Doesn't matter. It's the same. Okay. So this is what you find also in the slide. You can copy paste or I will also put in the Git the file. So you can easily copy paste. Architecture. So after the begin, we can simply do what we want, x and operator y. Okay. So and finally we save. Okay. So this is all we need. For our VHDL file. Now I open the pins. So I need to open the constraint file to set it. So let me copy paste it because this is a bit long from the slide. So let me put it in Git also for you, this file. Okay. Okay, so I put a folder in the Git with these two files in case you want to copy paste or add directly the file if you want. So just to show you, if you already have this and you want to add a new file, you can add sources from the panel on the left. So add the sources allow you to add the new constraint file, new VHDL file, new test bench. Okay. So if you want to add the new VHDL file, it's the one in the middle, and then you have the same panel as before. You can create a file or add the file, so and add it to the project. So I don't do it now. So I save the pins. So now we have both pin and VHDL file. So what we can do is just to launch. Okay, first of all, we can do the, just for fun, we can do the RTL analysis, okay, and see what he understood. So let's see RTL analysis. Let's see the schematic of this at the RTL level, so not at the component level of the FPGA. So here it's just what he understood from your code. So I pressed the inside, I clicked inside the RTL analysis schematics, and he will analyze the VHDL. Take a bit of time for a simple HDL, but so this is what he understood. X, Y, logical port type AND, Z, okay? So this is what we wanted, and this is what he understood. This is not the schematic of our circuit. This is a step before. It's just RTL analysis, a static analysis on your UHDL file. If we want to do to see the schematic after synthesis, well, we have the same option here. We have the possibility of opening the schematic here of the synthesis menu. But first we have to run the synthesis. So let's run the synthesis. So running synthesis design, let's say it should take 30 seconds or something like this. Okay, synthesis done. We can see the resources, one LUT. He used only one LUT for implementing the end port, that's correct. We can open the schematic of the synthesis. Okay, it's not the same as the RTL analysis. Why? So first of all, we can notice some new element. So we have input buffer and output buffer. This has been added to our circuit by the synthesizer automatically, because he understood that this port are mapped to external pin, because they are defined as input port of our top module entity, okay? So he added automatically an input buffer and an output buffer for entering inside and outside of the FPGA, okay? Then there is no anymore our end port, but there is a LUT with the 2 input and 1 output. This is why, because all the Boolean function, this is because all the Boolean function has to be implemented in LUT. But if we click on here, in the, so I'm run out of space. You have a truth table here. Let's open it bigger. Here we are. So if we look at the truth table tab of the LUT, we can spy what Boolean function has implemented in the LUT. Okay, and you find that this is called the truth table of the Boolean function. So you can see all the possible combination of input and the associated output. So only in the case 1, 1, we have the output at 1. In all the other cases, we have the output at 0. This is the end function, basically. So it has used the LUT, but inside of the LUT, it has been programmed with the end function that we want. Okay, so we are ready for the next step. We can run the implementation. So each time you execute a step, he will open a window. Sorry, first I have closed it quickly, but it opens a window proposing you to go to the next step, basically, to launch directly the next step, or to open the schematic of the present step. So but you can do it from the left menu in the same way. So now it should be okay, so he is implementing now. Okay, he has implemented, so we can either open the implemented design or go to the next step, generate the bit stream. So let's open the implemented design just for fun, also in this case, because it's an overkill what we are doing, of course, for a simple end port. So now here you have your FPGA, all the resources in your FPGA, and you can see what he has done. So here are the resources that are being inferred. So for example, if we want to spy the input X, we can mark it with a given color. So this is the pin for entering in the FPGA, okay? This is, I can zoom. Okay, so let's remove the mark. So this is the pad, physically the pad where we enter, and this is the my initial net. Okay. So here you can mark and choose the color. So you can do it with any resources. So for example, X, Y, Z. So these are the net. Then you have the cell. So the loot, for example, that we have used, it's this one. It's a loot2 type. So let's see. So this is the loot. We can mark it. We can see it, but let's mark it with a given color, yellow. It's here. So this is the output, and this is the input. And he has chosen that particular loot that is close to the input. He could have chosen whatever, probably. So, and here you see, well, let's zoom here. If we want to see the real path, we can enlarge and select the output pin, and this is the real path that the signal does. Please. These are the clock region. So the clock region. So if you want the clock distribution work, there is a global tree that then is divided in a sub-region, and then there are special buffer for the let's say remaining propagating the clock inside of the same region, and some other kind of buffer for making the crossing of a region. So let's say that if you have multiple clock region, it's better to distribute the clock, each region with a different clock, basically, and keep it separated.
Cheaper or easier to stay inside of the same region instead of cross?
Here, it's obliged to cross because we choose in the constraint file the output pin that is in another region, so it's obliged to do it. But usually, yes, I mean, all the logic, if the logic that you implement fit inside one region, he will leave it in one region. I just click on the, so this is our, so let's remove the highlight. Okay, so this is the slice you have seen in the slide before. So we have the for loot. This is the carry chain, and these are the 8 flip-flop at the end. Okay, so we are using only this loot, and we have 2 input. If I click on this, I highlight the path, the input path, the 2 input path, and this is the output path. Okay, clicking on them, you can highlight and see it. This is pretty direct. It's the output that is far away. But you need to zoom a lot before reaching this level, because this is the CLB with the 2 slice, and this is the 1 slice, 1 loot. So you can zoom it a lot. So look at here, you have the 6 input loot, only 2 of them used, and the 2 output, only 1 output used. Okay. So this is the game that we are doing because the circuit is super simple. Clearly, when the circuit is complicated, you can never do it. I mean, it's very hard to identify each part, even if sometimes it's needed. After that, we can do generate bitstream. So finally generating the configuration file. Yes, so just clicking on it. So for example, so now it's not working because I launched the, okay, here, just click on it and you highlight it. Oops. Then unzoom and you see it. I don't think this works. So the other option is to click on the name of the net and make highlight. Then you can put a color and you color it on the color you want. So this is the Z line output. The connection. So you have many switching matrix that you have to cross for arriving from the loot to the output. This is the output pin. So why it has chosen an output so far? It's our fault. We have put it in the constraint file that we want to use this LED, and this LED is connected to a given pin. So our input pin is here, our output pin is here. They are far from them, but we are forced to use it if we want this switch and this LED. So if you don't have put the constraint file, okay, let's have a look.
So we could pick it from the slide, but maybe it's not.
Yeah, also me, I put LED 4, which is closer to the switches, so it's
I used different pin.
I use different pin.
No, I don't know. Let me. have a look. H5. So let's have a look. H5. If it is the same that I used. It opened in the other screen. H5 should be. Then let's verify this because we have two different versions of Vivado.
We have it now from
100.
Ah, okay, that's the point. So
Because when I do highlight here and I oopsie.
okay, let's enable these.
I mean it's here. It seems,
so you needed to highlight with
Which is coming from
the output Z.
no, because we need to compare again.
What is that? What is that?
So these are net. This is the Z before the output buffer. Z is after the output buffer. So if we want Z, so let's mark it. Mark. Okay, it's here.
Okay, and if you want the line?
The line, yes. I like the. Yes, but should be highlight. You already did it? Ah, okay. And it doesn't display it. So let's see. Routing roles.
It also we got a notification that we cannot write into folder. I don't know if
It was an error message. Critical warning, yes. So let's cannot debug NetZ. It's not accessible.
Connected those
Like button 0, no?
Yeah, we get rid of the.
maybe H5 is not what we think it is.
The underscore?
Okay, so let me have a look.
We can also do the
Thanks.
Button 0.
We have to ignore
maybe semicolon.
No, it's correct. The last one should not have. So I think here it's fine. But this is an old message. Wait. No, this is not. It's an old one. So I think this is fine. Well,
like the crash for the second time or third time, I don't know.
let's go to the implementation.
Yes.
And people go
Device. So
the time is just reopening Vivado after you used it for 3 minutes and then crashed.
configuration.
Yeah, okay.
Could the bit string be, for example?
I guess maybe it was saved, but maybe can I just do this?
Yeah.
No.
What the complaint for why it crashed?
You know, I think that like I thought it would like kind of passing the data in.
Failed to open.
Abnormal program termination. So we can yeah.
Yeah.
Right.
Okay, so let's reopen the implementation.
You're gonna get a seizure. Stop, please.
Please, I don't want to see this PC again.
Okay, you are playing with the lens.
Yes.
Perfect. I mean, if that works, I understand how it works. Some memory.
So this is
You didn't
unable to create directory.
But I think you
Ah,
yeah.
but
We saved our project there, so I don't know if maybe we should look at.
yes, you cannot because this folder is root.
Oh,
It's only accessible by root, so the project should stay in your home,
okay.
in your own folder. I think this is the reason.
Okay, that's
Okay.
Correct. So I did the generation of the bitstream, so let's deploy it. Open Hardware Manager, connect the FPGA. Open target, auto connect. So now you should see here the hierarchy. This is your programmer. So basically, in our case, is the USB to JTAG switch that we bridge that we have here. Then connected to this bridge, we can find our FPGA. Okay, the 100 in your case, if you have the 100. That's an interesting part. So inside of the FPGA, you can find the XADC. So you remember it's the analog to digital converter that is always there. So you can also open it with a double click and look at the temperature of your FPGA. So this is a silicon temperature of the FPGA. So it's quite, it's not programmed also, so it's not doing anything. So it's normal that is 30 degrees. So let's instead program the device. It doesn't work.
Potrebbe non funzionare.
Okay.
Non si accendono i lettini.
It proposes you to a bit stream. If it doesn't propose you, the path when you find the bit file, it's inside the run subdirectory of your project, implementation, and then you find the bit file. Okay, program. And here we should have our program. Yes. So only if you switch on the two should. Let's try. Okay. Sure.
So actually, Carlo crashed twice. So we redid everything, and it's doing the implementation well, and then it fails and writing the bitstream.
Okay, with error. Messages. So let's remove, yes, we already removed. Unspecified standard. So this is a problem of the
We can put CMS, okay, 3.3.
yes, probably, yes, exactly. Yeah.
But the implementation goes well even without the constraint on the voltage.
It's writing a bitstream that stopped.
Okay,
Yeah. Because in the implementation he didn't have to specify. So the pin location, yes, but not the electrical standard.
We got until this, and then we didn't see what you did. So what did you do after having this?
Well, here it's just for fun. One can look at. Yes, you can see what to do next is generate bit stream.
So just click here.
Yes.
So we click here.
You already did it.
Yes, but then we just
okay, rerun. Yes. Okay. Okay. So here you can choose how many jobs you want in parallel for creating. If you have a multi-core, that can be, but that's fine. Doesn't change nothing.
We're looking at something here.
If you look at go to project manager. So here you should tell you what is doing running bitstream. So we have just to wait. The
and when this finishes, it automatically sends it.
No, we have to do. I will tell you.
Okay, that's
yeah.
So at this moment, everybody's just waiting for this.
No, I already did it. Yes, but let's redo it. Okay, so here you can do Open Hardware Manager.
Okay.
That is the server that connects there. Yes. Open Target.
Here?
Yes. Auto connect.
Oh, it's 2 monsters.
Yeah, fortunately, yes. Okay. So here you see the first line is the program, the chip that acts as a programmer for the FPGA is the bridge. Yes, exactly. Okay. And the second is the FPGA connected on the JTAG. You can have multiple of them also. Okay. In this case, we have only one. And the third one is the IP of the ADC that is always present inside the FPGA. So the one for the temperature. Yeah, exactly. So if you double click on this, you can see, press OK, the temperature of the silicon of the FPGA, so 38 degrees.
And it's communicating between these two through, I don't know what.
JTAG, yeah. JTAG,
okay.
And then USB, yes.
Oh, okay.
In principle, if you should see it increasing, but it's almost empty, the FPGA now, so it's not programmed. So
like you put like a heat gun, then it's going to start going up.
Yeah,
okay.
Exactly. So now you can do here with the program device. Yes, program device. And this is the bit file that it already suggested the bit file, the only one that you have in this project.
So this is what happened when we created.
Yes, exactly. That file, .bit.
And then just program?
Just program. Exactly. So now it's uploaded. So
we play with the switches.
Exactly. So this LED is the done, means that the upload was done. So now it's programmed and you can play with the switch.
Yes. Which switches are
the first two? Yes.
Ah, you see
okay.
here?
Yeah.
You see here? Oh, cool. Thank you.
I just want to check something. It says it's already upload, right?
Mm-hmm.
Okay.
To upload it, yeah.
This one is like it just saved into a file that contains 010.
Exactly.
Can I leave that? It's just like a normal text file or something.
You can I think so no, it's not a txt file, it's a bin, it's a bin file, but you can in principle see it. The only problem is that there is no mapping between the meaning of the bit and the functionality, so you don't know what corresponds to a given bit. But you can change it. So there are tools that actually take the bit file, the bit stream, change one bit, implement it, and see what happens. Change one bit, implement it. So brute force, yes. And they discover with brute force the meaning of each bit, what does in the configuration. So these are tools that are used for radiation hardness, basically, because for radiation hardness you want to know the mapping, because you want that the configuration file, the configuration bit that you use are far from each other as much as possible. In this way, if one is affected, it affects only one and not all the part close to your bit, basically. So But yes, it's not an open source FPGA. There are also brands of FPGA that are open source design, and they allow you to understand what each bit is doing. You're welcome.
I use different and I make
But I felt better until I didn't. No, I think it's because this is
Yes.
Yeah, this temperature sensor, is this like on the FPGA itself? Or
Yes.
is this implemented
No,
on the
no,
board?
in the FPGA itself.
Okay.
Yes, yes, it's internal.
And now, for example, at the like vector here, when there's many FPGAs used,
Yes.
do they all come with their custom board, or is this like a huge thing with like
So usually
thousands of these chips?
we build the board. So we build our board, and yeah, I mean we for controlling it basically usually use actually processors for reading the data. So the Zinc is very used as an FPGA, so it's the one that combines processor plus FPGA. So you can easily install Linux on the processor, then SSH on your FPGA, and check the temperature of the hardware.
So people are actually then programming then via SSH into the CPU.
Yeah. Also, the CPU part can really, you can just copy the bit file and download it from the FPGA itself, from the CPU inside the FPGA.
So the entire program is actually done, can be done at your own laptop via SSH.
Exactly. Exactly. So it's very practical.
Ah, cool.
I mean, it kind of makes sense actually.
Yes.
I have a question. So
Yes.
like, is every variable like a global variable? Because the same name
Yes.
used here automatically was picked up as the X of the other.
Yes. Yes.
So are the names global for the entire program?
Yes, we will see there is some region that that are special environment that are called process. We will see it, and if you use that, you can declare local
Like a
scope variable for this environment. Otherwise, they are global.
Global and
Yes.
everything gets picked up. So if you accidentally use the same name, it messes the entire thing.
Yes.
Ah, okay.
So usually, if in this case you will have an error that says that you have multiple drivers for the same net, basically.
So
So
if you, for example, add another one of these also to port another
Control Z again.
it will complain.
It will complain.
Ah, okay.
Yes, it will tell you you have a multiple driver for the same line.
Great. Very cool. Thank you.
You're welcome. So So let's do the modification that I proposed at the beginning to use another way of describing the end port and see what are the difference. So let's come back to end. It opened in the other screen. Okay. Okay, so let's replace this line. Well, actually, so I've pushed in the Git the file, the complete file. So what I want to do, it's this.
Is there anyone else who needs a laptop? Yes. Yeah, you have more FPGAs.
I have two, one more.
One is broken.
One is broken. One more. So broken or the LED broken? We don't know.
I don't know. Nothing turned on.
Okay, we will check it.
And,
Which one of the two?
Also, Vivado didn't see it.
Ah, then it's a major fault. Yeah.
I don't know, maybe it's just
The cable.
USB port.
USB port.
It wasn't the cable because we tried without cable and without a PC.
Okay, we will check it. So this is my modification. So I introduced this thing that in VHDL, that is the internal signal. So you have the port X, Y, Z in this case. Now I defined another signal that it's only used internally to my circuit. So it's not a port, it's an internal signal. So this has to be defined before the begin. So before the begin, you have to define all the hardware pieces that you want to use in your design. So I declare an internal signal. I call it input, and I don't have to give the direction because this is not a port, it's internal. I just have to give the data type. So the data type is standard logic vector 1 down to 0. What does it mean? It means that it's 2-bit. And this is the complication, another complication, with respect to what I told you before. So here you have the possibility of declare the vector as 0 to 1, 0 to n, or n down to 0. So what does it mean? It means that so it's the difference between little endian and big endian. So it depends on how you interpret the bit order. So in one case, 1 down to 0, 1 is the most significant bit, 0 is the less significant one. 0 to 1 is the opposite. 0 is the most significant, 1 is the less. So the most used is this convention, with the most significant down to the less significant. Why this is? Because if it's for representing a number, basically. If I have, let's do a simple number. If I have this 4-bit, I want that this is bit 3, this is bit 2, 1, and 0. Okay? In this way, for me, this is number 8. Okay? It's in binary, number 8 in decimal. If I read it as a 0 to 3, this is bit is 1. This represents number 1, sorry. Okay? So if I want to read from left to right, I need to use the convention with the down to. If I want to read right to left, I use the to. Okay? So usually most of the people write down to. Okay, so I declare a 2-bit vector input. Input is the concatenation operator between x and y, so it's 2-bit. So in this case, bit 1 is x, bit 0 is y. And when this concatenation is 1, 1, I assign 1, otherwise I assign 0. Okay, this is what we have seen. So another important point is that look at these two statements. These are only two statements, but the order of the two doesn't matter. So in C++, in Python, you would have put this before the other. So because it's a sequential language. VHDL is a concurrent language, completely parallel. So all the statements are executed in parallel. Real parallel because the hardware works in parallel. So doesn't matter the order. It's maybe more difficult to read, but actually doesn't matter. So I think that we can see the analysis of this and ask for RTL analysis. So this is the old one. Why it doesn't? So I didn't save, sorry, save. RTL analysis. Run again. Reload. So now he's interpreting what we have written. So look, it's very different to the one before. Before was clearly an end port. Here, the structure, it's a multiplexer. She understood that we want to describe a multiplexer because we have used this when else clause. So this is basically, he understood we want a multiplexer. As a select line, we use 2-bit that are x, the concatenation of x and y. And this allow you to choose either the value 1, either the value 0. So depending on the status of x and y concatenation. So if both bits are 1, we choose 1. In all the other cases, we choose 0. So this is what he understood correctly. So the RTL analysis is different because the code is different. Now we run the synthesis again, and what we have to verify is that the output of the synthesis instead should be exactly the same as before. Otherwise, the compiler means that the compiler didn't understood. Non so quale sia quella rotta. Try.
Quella con la scatola più bella.
Ok. Yes. It's already on Git also. So now let's open the generated synthesis schematic. Reload. Okay, luckily this is exactly the same schematic as the other description. So even here you can check the truth table of this LUT, and it's the end port. So from now on, if you do implementation generated stream, of course it will implement exactly the same code. Okay. So let's have a look to this. What's okay? Completely dead.
Not the bandwidth. Yes, please. I love that. Okay, that's maybe like a sample. Okay.
So once you change this to be the different, like with the,
Yes.
then when you click the schematic, it showed you something different.
Yes, because this is the old one, then you have to reload. No, reload is here.
Oh, here.
Mm-hmm.
Ah, okay.
So it has opened the previous.
So saving is not enough. Like you have to.
It has to. So it's reloading the output of the synthesis basically. So you have the output synthesis of the previous population.
And then just one question.
Yes.
You said here standard logic vector 1 down to 0.
Yes.
That makes it 2-bit.
Yes.
So if I say, for example, 10 down to 0.
It's 11 bits.
11 bits.
Yes. Because
Little Indian. or is that?
I don't remember which one is. It means the most significant on the left. Yes.
So 11, 10, 11.
Exactly.
And if I do it 0 to 11,
It's
it
the
will be
opposite.
0, like
Yes.
beginning. Okay.
Yes.
Okay, thank you.
You're welcome.
If we put 0 to 1, what will happen? Is it possible to
Yes, yes.
0 down to 1?
No, 0 down to 1 is an error. It should be 0 to 1. Yes. And
in this case, it doesn't matter, right? Because the end of the two.
Doesn't matter. In this case, doesn't matter because we are not interpreting as a number. So we don't do arithmetic on it.
But it will change which. Oh, well, it's an and, so it doesn't matter. Okay.
Yes. Yeah, also, that doesn't matter. But okay. Yes, you will have on the left basically the 0, on the right the 1. If you do the concatenation, the order matters. It's x and y, or y. In this case, the operation that we are doing is symmetric. So.
But if I say, for example, 0 to 10. Right?
Yes. Yes.
And then I say equals string 1 0 0 0 0.
Yes.
To assume it's the other way?
No. It's assuming that
1 0 0 0.
Yes.
But still puts the high bit, the most significant.
No, if it is 0 to 10, on the left you have the 0, on the right you have the 10. 10th.
Okay, but if okay,
So also this is mind blowing when you assign. You can do a bit swap. So if you assign a vector, define the 10 down to 0 with the vector that is 0 to 10, he will do the bit swapping basically.
So let's say I have, let's say input 1, just to play input 1, and then I say 10 to 0, right? Can I have another one?
10 to 0, yes.
Input 2,
yes.
Same thing. Logic vector 0 to 10,
yes. Right. And then you can assign one to the other.
Then, no, but if I say, for example, input 1,
yes,
equals, and then I do 1 0 0 0 0 0. Let's assume it's whatever. And then if I do input 2, and I do 1 0 0 0 0 0 0.
They are not the same.
They are not the same.
No, they are not.
They are the one
swapped. Yes.
They are swapped.
Yes.
So which one has the one? Which one has the one on the left?
The one. So
the 10 down to 0.
So this has on the left 10 and on the right 0.
Yes.
And this has 0 on the left and 10.
One on the left. Okay.
Yeah.
Okay.
The 10th.
Okay, I think, okay.
The address 10th is on the right.
Okay, thank you.
You're welcome.
I don't know why the Europeans heard it.
Una domanda. Come si fa a fare una implementazione su una parte ridotta del progetto?
Sì, non saprei neanche rispondere onestamente a questa domanda, nel senso che non ho mai fatto la riconfigurazione parziale, quindi non, operativamente, cioè l'ho fatto per il PCI Express, però lì è molto semplice, c'è una cosa che si chiama tandem, e diciamo è una configurazione dell'IP, e allora sì, in realtà cioè, ho visto un po' come si fa con Strain, cioè bisogna definire delle aree, una volta che è stato implementato, cioè nel constraint file si mettono, diciamo, si definiscono proprio delle aree, delle regioni dell'FPGA.
Do you want to listen?
Si definiscono delle regioni dove si dice quale logica è contenuta in quelle regioni, quali blocchi, e dopo ci sono dei constraint di ordine delle regioni, cioè io carico prima questa regione e poi l'altra. Mi immagino che sulla riconfigurazione parziale devo fare una cosa simile, cioè, però non so come triggerare la riconfigurazione, cioè mentre lui questo lo fa in sequenza, cioè nel tandem, lui carica una regione e poi subito dopo, appena finito, carica l'altra.
Una potenzialità dell'IP, del PCI.
Sì, esatto, viene integrata lì, però quello che quando uno flagga che vuole usare il tandem, genera un constraint file sostanzialmente con questo, e se ci sono altre cose, cioè questo non sa il resto del design che cosa ci sia, quindi nei constraint bisogna ingrandire la regione che è fuori dal PCI Express, sostanzialmente mettere dentro tutto il blocco. Però è una feature, diciamo, c'è un constraint che fa in modo che questa venga caricata immediatamente dopo. Mi immagino che nel caso invece di riconfigurazione parziale bisogna intervenire con un tickle script, perché è lo script che si usa per il TCL per comunicare dopo nel JTAG alla fine, per poter triggerare la riconfigurazione, però penso sia comunque da dividere in aree, però non l'ho mai fatto.
Okay, cosa faremo nei prossimi giorni su questo?
Altre cose, facciamo esempi semplici, giusto per vedere il VHDL, quindi istanziamo flip-flop e poi facciamo counter, state machine, cioè cose semplici. Poi facciamo la UART, cioè quindi ci colleghiamo con l'FPGA e facciamo l'UART protocol, possibilmente fatto da voi, cioè creare il blocco dentro l'FPGA che fa questo. Poi se abbiamo tempo, a me piaceva fare un TDC, un Time to Digital Converter, quindi uno semplice a oversampling, cioè usare il blocco di I/O per samplare rapidamente e fare un TDC, insomma. Questo dovremmo riuscire. Poi non so, ho portato anche dell'altro hardware, abbiamo tipo dei mini pod per fare audio.
Okay.
Quindi io di solito nel corso che faccio fare agli studenti un filtro digitale per l'audio, uno può fare effetti digitali tipo eco, robe così, insomma, se abbiamo tempo. Please.
I have a small question.
Sure.
This bitstream that you use and the program, the FPGA, is this always the same length?
Yes, because it depends on the FPGA part number. So it depends on how many resources there are.
So then if I just do this very simple logic operation, or if I do a very complicated machine learning network,
yes,
it always take the same amount of time to program it?
No, to generate the bit stream, No, it takes less time for generating it. The size of the bit stream for downloading it, yes, it takes the same time. Yes, yes.
Okay, I'm interested.
Yes. There is a constraint used for bitstream compression. If you use that, I think that will change in the size of the bitstream.
I see.
But you need to specify that you want compression. In that case, probably if the FPGA is empty, it will take less time also to download.
Then you probably need to really know what you're doing.
Yes.
Thank you.
You're welcome.
Un'altra cosa
Sì.
che non c'entra niente con la lezione,
Sì.
non è che ha qualche documentazione utile per timing constraint dinamici?
Dinamici? Che senso?
Allora, non è per me in realtà,
Sì.
io non lavoro tanto con le FPGA, però noi ne abbiamo una nel progetto, abbiamo dei problemi di timing constraint per un LVDS che va molto veloce. A quanto pare usiamo una Kintex Ultra Scale e a quanto pare settare i constraint statici, che non so bene neanche cosa significa sinceramente, non è abbastanza, ma c'è quest'altra possibilità di usare time constraint dinamici per riadattare, perché il problema brevemente qual è? Che il problema è che noi abbiamo, cioè in fase di implementazione, a seconda di quanto vengono lunghe le piste, non soddisfa, cioè i timing, il constraint di timing non sono abbastanza per soddisfare le nostre necessità, diciamo. E io so
Ma
che c'è
su un input praticamente, cioè voi dovete semplare un input.
Esatto, cioè non fa il diagramma più bene, insomma. Quindi,
Okay.
e io avevo letto che c'è questa possibilità di fare constraint dinamici, nel senso che riadatta tipo in tempo reale, una cosa del genere.
Cioè, allora, io questo non lo conosco, però solitamente il problema qua è se uno ha differenze tra un'implementazione e l'altra.
Sì, esatto.
Allora, questo significa che manca il constraint che dice di usare il blocco di I/O, perché normalmente questo non dovrebbe esistere, perché se io prendo l'FPGA e diciamo, parto con un mio input messo in questa posizione qui, adesso se in un'implementazione il flip-flop che va a semplare questo è qua, o è qua, chiaramente lo samplerà in modo diverso, quindi diciamo, soprattutto se nell'applicazione non so il ritardo di questa linea, perché ci sono dei constraint per definire qual è il ritardo.
Definiti perché sono scritti è un modulo, quindi sappiamo le lunghezze delle piste, quindi in teoria quelli sono definiti.
Ok, però dopodiché diciamo conosco la fase qui, però non conosco, a seconda dell'implementazione, potrebbe cambiarmi. Allora ci sono due modi: o decido di mettere un constraint di lock, sostanzialmente di posizione sul primo flip-flop, e allora in quel caso lì sono sicuro che sceglierà sempre questa posizione, e il path non sono sicuro neanche, in realtà, a meno che non vado a fare un lock, posso fare anche un lock sul specifico path, in modo tale che non ne scelga un altro. Però diciamo questo è il modo non corretto di fare, cioè il modo corretto sarebbe di dire usa il flip-flop dentro l'IO block, perché ogni IO block ha diversi flip-flop, che non sono nelle CLB, cioè proprio sono specifiche nell'IO block. Allora, se io uso questi, sono sicuro che non ho routing praticamente ed è sempre uguale la compilazione. Poi il flip-flop successivo può essere ovunque, per me non importa, l'importante è che il primo dove lo samplo sia quello corretto. Non so se questo è il suo problema, però...
No, allora, è il problema del mio progetto, non ci lavoro io, però so che c'è questo problema qui, quindi magari adesso chiedo questa cosa perché sì, ok.
Cioè adesso se ne arriviamo a fare il TDC non è altro che un campionatore e istanziamo il blocco di I/O e facciamo l'oversampling qua dentro, non in un flip-flop generico. Ecco.
Va bene, grazie.
Niente.
Can I ask you something?
Sure.
I'm confused by this when we have this, right?
Yes.
And you say the order doesn't matter because these things happen in parallel.
Yes.
But I'm a bit confused because, well, this has to definitely happen before this because otherwise you don't have anything here, no? Like
This is a circuit, so you cannot say that it happens before. Yes, it happens before in the sense that when you, yeah, I mean, when you draw this circuit, I would not say before, I would say at the same time, in the sense that here we have, the circuit was the multiplexer, and this concatenation, this is X and Y for the select. Then here you have the 1, and here you have the ground. And when this is 1, 1, you select this line. So 1, 1, sorry. And all the other.
it's like,
So
you have to think about it like a circuit more than.
I mean, this and this happens at the same time for me.
It just runs.
Yeah.
Yeah. Okay. Just because like naming it as a variable
yeah.
is like this has to go in here. But
That's
okay,
true. That's true. But
I
then,
understand your point. Okay.
so this is int. This is int. What do we call it? Int input. Okay. So this is just a signal, and
then okay, sure. It's like okay.
yeah. So yes, it's a little difference between imperative language like C++ and parallel language. So this is the more similar to declarative language.
Okay, thank you.
Yeah, right.
That's my job. Exactly. So you're basically we have a lot of clients. I have a lot of clients.
Yes,
Questa non va, l'ho appena aspetti, questa è quella che uso, questa era quella dentro la scatola 40 e non va. Quella che ha preso era la 18